Okay. Oh, cool. Are we 2 minutes behind now? I'm not thrilled with that. I hope we're not 2 minutes behind. Ooh, okay. I don't think we're 2 minutes behind. Okay, fantastic. We got it. We're live. Okay, sorry about that. Sorry to keep you waiting. This is my first live stream in a very long time, so hopefully it gets better from here. The plan is to do a few of these, so we'll see how that goes. So again, we're looking at January 2023. And the idea here is that we want to do all 85 questions. But before we do that, I want to take a look at this scoring guide because it kind of sucks, honestly. I'm going to be totally honest with you. Okay, so the raw score is the number of questions you get right out of 85. Chemistry exam, every single question is worth the same number of points. So they don't just do like a percentage score. They are going to use not this conversion chart. They make a new one for every test, but they're going to use a conversion chart to figure out exactly what your score needs to be. So if you say, for instance, you got 35 questions right, like this right here that I can't highlight just now. What is going on? Cool. I love this. If you get 35 questions right, your score would come out to be a 54 on your transcript. So for most of us, 65 is passing, which means you have to get 50 questions right. My least favorite year of chemistry exams, in order to get a 64, which means like you just missed passing, there were 2 raw score options that converted. And that happens here. So like if you get 44 questions right or you get 45 questions right, you're still going to only get a 61 on the test, right? So basically the 45th question that you get right doesn't count. It is going to happen whether you get 64 or 65 questions right. That both of those are going to translate to a 75. I feel like this one is not so bad, but they used to be way worse. So that's just something to consider, that if you are sitting there counting the day of the test and you're like, okay, I feel like I definitely got 62 questions right. 62 questions right would translate to a 73, not to, let's see, a 62 out of 85. That comes out to a 73. So that one actually does work. Usually in the 70s, they do work. But let's say you did 80 questions right. 80 out of 85 is a 94. They're only giving you a 92. So we don't love it. So just wanted to make you aware of that. Typically, we're going to need 50 questions in order to get the 65 to pass. And that's that. This is the answer key. They call it a rating guide. We're going to reference this as we go. And we have our reference tables. We got all of them. We have the answer booklet. The links to these things should be in the description of this thingamajig. We're going to get started real quick. Okay, chemistry test, part A. Okay, so the part A questions, typically they are things that are pretty simple. They are often just going to, why is this not wanting to work? Oh, this is cool. My cursor doesn't want to go all the way over. Why is that? That was strange. Okay, I'm writing with like a little tablet here. And for whatever reason, it's getting jammed. Okay, that also has never happened before. Again, part A questions, the first 30 questions are typically going to be like straight up definitions, concepts that you were supposed to have kind of sort of memorized, and things that are like really quick to look at with the reference tables. Sorry, this is like definitely in my face. I'm sorry, that was probably really annoying to listen to. This is my husband's setup. I'm not very good with this kind of stuff. Okay, so for question 1, oh boy. Question 1 is typically going to be an atomic structure question. The question is just, what are they going to ask you? A lot of the time it's going to be charge of a proton, charge of an electron, location of a subatomic particle. Rutherford is definitely going to show up on the test. Pinky promised you that. So this question is asking, which conclusion was developed as a result of the gold foil experiment? And the gold foil experiment, we know, is Ernest Rutherford. And he says a few things, right? He's shooting the alpha particles at the gold foil. And he finds the teeny tiny, small, dense positive nucleus. And he knows that it's teeny tiny and that it's positive because he is launching positive alpha particles at the sheet of gold foil, just like aluminum foil, but made of gold. And most of those particles go straight through and they hit the back of his detecting sheet, which is making like tiny little pinholes. So he knows that they're hitting in the back. And when this happens, he's realizing the atom is mostly empty space. There are a few of those particles that kind of like come in and go out to the side. And because the stream of alpha particles is positive, he knows that they're avoiding something positive inside the atom. And then a teeny weeny amount go and they kind of like bounce backwards. And because it's such a small number of things bouncing back, he knows that the nucleus has to be very, very small. So atoms are made of mostly empty space. That is true, and Rutherford said that. Atoms are hard, indivisible spheres. This is not true, but we thought it was true when we were talking with Democritus and John Dalton. That's what they thought, and it turned out that that was no good. So at some point, we thought that was true, but it's certainly not. So we're going to cross that out. Atoms have different volumes. That is true. They take up a different amount of space. Like hydrogen is a lot smaller than, I don't know, uranium. But that has nothing to do with the gold foil experiment. And then finally, all atoms have the same volume. That is the opposite choice of question 3. My strategy is to not usually pick the things that contain opposites, just because I find that they are often not a good answer choice. So atoms are mostly empty space. That is what we're going to go for this particular question. Question 1 is answer choice 1. Atoms are mostly empty space. Now, this is my first time using Cami, and I would like for this to be slid over a bit, and I don't know how to do that. And tool, can I? No, I want to slide you over to the side. Because for whatever reason, my tablet doesn't like this edge. It's okay. We'll work with it. Okay. Question 2. Which two particles have a mass approximately equal to 1 atomic mass unit? This one is mostly memorizing, but this one should be on the reference table. That's not the one we want. Let's zoom in here. Okay, right here. We got protons, neutrons, and beta particle is just fancy chemistry for electron. You can tell from that little E right there, that is for electron. And we do not care. Thank you for disturbing us. The numbers on top, remember, are mass numbers. And the numbers on the bottom are atomic numbers. Or charge, kind of, sort of. So in hydrogen or in a proton, we are looking at a mass number of 1. I'm going to zoom in a little bit more. And does this thing have an eraser? How does Cami not have an eraser? Very strange. Okay, this one right here is the atomic number, or the charge, kind of the same thing. Ooh. I don't know if it's the tablet or if it's Cami. Did I just say that on the top? No, the one on the top is not the atomic number. The one on the top is the mass number. The one on the bottom is the atomic number. So let's draw that. Ooh. The top is the mass. Okay, so in a proton, which is the same thing as a hydrogen because they're both made of one proton, the mass on the top is 1, and the same is true for the neutron. That's the mass number on the top. It's 1. And that means 1 atomic mass unit. Now, on the electron, where we have 0 and -1, that 0 doesn't actually mean 0. It's just that electrons are so tiny that we don't measure their mass. So it's effectively 0. Think of it like significant figures. It rounds to 0. We'll say that. Electrons actually do have mass, though. So going back to the test, particles with approximately 1 atomic mass unit worth of mass. We are looking for the answer choice that has proton and neutron, which is choice 4. Choice 3, the electron is too small. 2, the electron is too small. And then choice 1 rather has this positron here. Positrons are really just positive electrons. They are not the answer unless we're talking about nuclear chemistry. So that's out. And here, question 2 is answer choice 4, proton and neutron. Okay. Question 3, an excited potassium atom emits a specific amount of energy when one of its electrons moves from where to where. Okay. This is one of my favorite types of questions because this one I like to call the Sesame Street question. And that is, which one of these is not like the others? I know that's dumb, but let's roll with it. For choice 1, we have an electron moving from the first shell to the fourth shell. So the shells means like the levels, the Bohr levels of electrons. The first shell is the one that's right after the nucleus. So we got the nucleus, and then we're going to build out, and we're counting 1, 2, 3, 4, 5, 6. There's only 7 of them. So when we're going from the first to the fourth shell, we are going from 1 up to 4. Then we have option 2, where we are starting at 2 and we're going up to 4. And then for question 3, or rather choice 3, we're going from the 4th up to the 5th. And then in option 4, which is the correct answer, we're going from 4 down to 2. Notice how 3 of these answer choices go up and 1 of them goes down? That's an indication that this is the correct answer. The Chemistry Regents Exam loves to do these Sesame Street questions where it's just finding the odd answer out because a lot of chemistry is this or that. It's endothermic or exothermic. It's positive or negative. It's covalent or ionic. It can't be both things at the same time. So your electron can't go up and down at the same time. So really what's happening here is that when you excite an electron, the electron is absorbing energy. A lot of the time it's heat in the flame test. You can also do it with electricity. The electrons are going to absorb energy and they are going to launch themselves up to higher energy levels. Eventually, because electrons are negative and protons... I just had a package delivered. Electrons are negative and protons are positive. The electrons are going to be called back to the nucleus. I don't know how to mute this. I'm sorry. The electrons are going to be called back to the nucleus because they're attracted. So the protons are going to attract the electrons. And when that happens, the electrons have to release that energy. They're going to release it in the form of visible light. Visible light just means it has a color. And that's how you get the color for the flame test. But then you can read the wavelength of that visible light that comes back and get the spectral lines. The color that comes back is not unique. Calcium, strontium, like a bunch of metals are orange, a bunch of metals are red, a bunch of metals are blue. When you get the spectral lines, though, you are going to get an exact answer of what your element is. I know that this doesn't have very much to do with this particular question, but you are going to have some type of electron excitation question there, and I want to make sure to cover everything. Okay. Question 4. Thank you, honey. A mailman. Question 4. Which list of elements includes a metal, a metalloid, and a noble gas? Okay, this means we got to look at the periodic table, and we're going to do this by process of elimination. So if we go to the periodic table, day of the test, you can write all over this stuff. Clockwise, please. Okay. Can I do 2 tabs at once? I want the exam. There we go. And I want the reference table. Sorry, loves. Ooh. Okay, and let's scroll this over. Okay, we're looking at question 4, and we have a periodic table here. Okay, there we go. Table S. Anybody else have opinions about table S? Can't stand it. Okay, we're looking for a metal, a metalloid, and a noble gas. Okay, so in case you forgot, this line... Oh, wait, I need to be able to draw. Oop, come here. This line right here is the staircase line. I probably should not do this ugly, right? I should probably try to do this nicely. Anyways, the staircase line is where the metalloids live. If a box on the periodic table touches 2 sides of this staircase line, it is a metalloid. There is one exception to that rule, and that is aluminum. Aluminum is a metal. Okay, I would not include polonium just because polonium's radioactive. In my brain, it's a radioactive metal, not a metalloid. Because it's radioactive, it doesn't really have the same properties as all the other metalloids. That's why. Okay, so in order to find the metalloid, we're looking for something that touches the staircase line. That would be boron. Come on. Boron, silicon, germanium, arsenic, antimony, and tellurium. Polonium does not typically count in that space, okay? The metals is everything to the left of that staircase line. Non-metals are everything to the right of that staircase line, but hydrogen is also a non-metal. It's lifted away from this group specifically because it's a non-metal, and this lithium and everything below it are metals. Okay, so running through this list, we have rubidium, which is a metal. It is the member of group 1 right, come on, right here. That is rubidium. Chlorine is right here. This yellow is not a good choice. You can't really see it. Let's do orange. Okay, so we have rubidium and chlorine. Then we have neon. That is a metal and 2 non-metals. Specifically, chlorine and neon are gases. So that choice is out. Now, if we go back here, strontium, metal, silicon, non-metal, I'm sorry, metalloid, radon, non-metal. That is the answer choice. But let's keep looking for the purposes of learning. Question, or rather choice 3, we have radon, chlorine, and neon. That's 3 non-metals. Radon is radioactive, so there's that also. And then we have silicon, the metalloid, rubidium, the metal, and strontium, another metal. So that is going to leave us with choice 4. I'm sorry, choice 2. Strontium, silicon, and radon. Okay, and here's another reference table question. Okay, so maybe we should mark this. Going back, question 2, we use, what was the name of that table? Table O? Yes. This uses table O. This one kind of came from memory. This is the periodic table. And then question 5, we're going to use table S. Okay. Which element has the lowest density at 298 Kelvin? and 101.3 kilopascals. That really means room temperature. 273 is standard temperature. 298, 300, that's floating around room temperature. 101.3 kilopascals is standard pressure. So that just means like regular life. The thing with the lowest density would be a solid. None of these are solids. Each of these answer choices are gases. So we're going to have to look them up and compare them, which means that this isn't really a chemistry question. This is a reference table question. And they very well could put this question like on an SAT and just make it a chart reading question, right? Okay, so density is this second to last column here. And argon is 0.001633. I think I would rather type this. No, I don't want to type it because it's too big. Oh boy. I wish my tablet would write better. Okay, we're going to draw for argon 0, well, the decimal right there. 0.001633. And then fluorine is up here, 0.01553. One, 5, 5, 3. I don't like this Cami app either. My favorite app to write in is Canva, but it's not easy to get a PDF into Canva. Okay, nitrogen is right here, so that is 0.001145. And then oxygen should be right below that, yes. Come on with this thing. 0.001308. We're looking for the lowest density. So the lowest density should be nitrogen, right? Honestly, here's what I would do, because day of the test, you're going to be stressed out, right? So you're looking for the smallest number. Everybody has a 0 first. So we're going to 0, 0, 0. Okay, can we stop with that flag? Stop with the flag. Everyone else has a 0 for the second number after the decimal, right? Okay, now the next number after the decimal, all of them have a 1. Okay, and now we're at the fourth digit after the decimal. Fourth digit after the decimal, the smallest one is nitrogen. 001145. So day of the test, when you're stressed out, you can look at it that way. Nitrogen. Okay. And that's how it's done. You look it up on table S. Okay. Whoop. There we go. This one is a definitions question. Which phrase describes the crystal structure and properties of two different forms of solid carbon, diamond and graphite? Okay. This is referring to allotropes. Allotropes. That is the vocabulary term you would want to look at. Allotropes. They are different from isotopes and they are different from isomers. Really what they mean is two different forms of carbon. So it's the element carbon. Graphite comes in these like hexagon sheets and it slides one off of the other. Think of like, not quite like a honeycomb, but kind of like a honeycomb, but it's flat. So you slide over the paper and these little hexagons are all over the paper. Then diamond, you have all of these like interlocking carbon things. And that's why diamond is very, very strong. So ozone, O3, and oxygen, O2, that's the other example that the Regents exam uses all the time for allotropes. It's just different bondings of atoms within an element. okay? Like different structure. Not quite bonding. I shouldn't have said bonding. But they're just built differently, okay? So in this case, we have, they're going to have different structures. You don't even have to know what the structures are. You know from being a human being and probably from taking earth science that diamonds are a 10 on the Mohs hardness scale and graphite is very, very low. You've broken a pencil before, you know this. They have a different structure. If they have a different structure, they have to have different properties. End of discussion. That's just the way that it works. Every chemical property that there is based on a molecular structure, like how the thing is built. Different structure is going to give us different properties. That is why when you get into organic, the isomers, where you have like the oxygen is either on the end or the double bonded oxygen is somewhere in the middle, you get a ketone or an aldehyde. They are different. They're different because that oxygen has a big old electron cloud kind of like crowding everything. And for that reason, it's going to have different intermolecular forces, and different intermolecular forces are going to give it different properties. That's a lot to say that they're just different. But they are. Okay, question 7. Which element has chemical properties most similar to sodium? I know, without even looking, that sodium is a member of group 1 on the periodic table. Do this. You go this way. Okay. And if we look at this right here, slide over, baby. Okay. Sodium is Na. Sodium is going to have properties most similar to other members of its group because they each have one valence electron. That's the big thing there. So the other member of group 1 is rubidium. Now, if I were writing this test, which lucky for you, I'm not. They did it. I would assume that there's going to be some kid who thinks that S is sodium, and then you put oxygen in that because those two are members of the same group. So if you are unsure of sodium's symbol, remember you can look that up on table S as well. So you scroll through, sodium, that's Na. Oh, good thing I looked it up because I forgot. You have 3 hours to take this test. Where's my calculator? 3 hours is 180 minutes. 180 minutes divided by the 85 questions puts you at over 2 minutes a question. 2.12 minutes per question. What is 0.12 of a minute? 2 minutes and 7 seconds. Woo! 2 minutes per question. You don't need 2 minutes per question. You'll be fine. You can take the time to look this up. Don't feel rushed. If anything, you should take all of the time in the world to do the part A questions because that's 30 questions. If you can get 28 out of 30, you're in good standing because out of the next 50, you'll only have to get 20 or so questions. Okay, so you really don't want to have like a flub on the first 30 because those are going to be the ones that are reference tables, definitions, not necessarily, there's no math for the first 30 questions. So it's not a lot of thinking outside the box. You want to make sure that you get those really, really well. Okay. Next up, question 8, which substance contains elements chemically combined in fixed proportion? This, again, is a definition. They are giving you the definition and asking you to know what the term is and then apply that term to the answer choices. So substances that are where you have elements that are chemically combined in fixed proportion, that is a compound. The fixed proportion means that for every 2 H's, you get 1 O, and you get a formula H2O. The opposite of that would be variable proportion, and that is something like salt water. Salt water can be very salty or just a little salty, and that's, you can vary the proportion. You can have more salt or you can have more water, and that's going to change the composition. Fixed proportion is the definition of a compound, and then it's asking you which of these is a compound. So it's just like a harder way to ask you a vocabulary question. If you need to, you can look up all of these on table S. Manganese, silicon, and strontium are all chemical elements, meaning that they cannot be compounds. They can be part of a compound, but they themselves are not compounds. Methane is the correct answer. You should know the formula for methane. It is CH4. It's an alkane, and it's a compound because you got 1 carbon bonded to 4 hydrogens. Boom. Okay, question 9. Which property can be used to differentiate a 50-gram sample of potassium nitrate at STP and a 50-gram sample of sodium chloride at STP? Ooh. Okay. Mass, obviously no, because they're both 50 grams. They told you that in the question. That's kind of silly. The temperature. Guess what? You are at STP. That means they are both at standard temperature. They are both at 273 Kelvin or 0 Celsius. So they have the same temperature, meaning you can't distinguish them. Now, phase of matter. They also told you this in the question. You are dealing with solid potassium nitrate and solid silver chloride. So they're in the same phase of matter. So that's no good. The answer is solubility. If we were to, and if you wanted to double check, I mean, obviously it's solubility because that's the only answer choice that's left over, right? But we know it's solubility by looking at, what is it, table E or table F? It's F. And let's rotate this back. Okay, table F. Potassium nitrate has the formula KNO3. And silver chloride is the formula AgCl. I don't know why these are so wiggly. I use this tablet all the time. If you watch like the regular YouTube videos, you know I write on this tablet. I don't know what's going on. So if we look at the solubility guidelines, K is a member of group 1. Potassium is a group 1 ion. It's always going to dissolve no matter what. It doesn't matter who it's bonded to. And the same is true for nitrate. Nitrates love to dissolve all the time with no exceptions. So then we have silver chloride. Halides usually like to dissolve, but if it's bonded to silver, it won't. Okay. When it comes to reading this table, I like to tell students to put a big line in the middle to help you remember that these are 2 separate tables. It says it's table F, but it's 2 tables with 2 different titles. On the right, you have insoluble compounds, so things that don't dissolve, with a few exceptions here. And then on the left side, you have things that love to dissolve with a few exceptions. And then, if you go like this, oh, come on with this thing. I don't know if it's this computer, if it's Cami. Okay, if you put a circle right here, those things, if any of your ions fall within that circle, it is insoluble. It will not dissolve. Okay, and then if it's outside the circle, it will dissolve. So in the circle, it is insoluble. And silver chloride, the silver pulls the chloride into the circle, making it insoluble. Silver chloride will not dissolve. KNO3 will. Okay, so that was a table F question. Okay, next up, 10. Which type of bond forms when electrons are equally shared between 2 atoms? This again, it is giving you a definition, asking you to figure out the term, and then apply that term to the answer choices. So the type of bond that forms when electrons are equally shared between 2 atoms. Okay, so if we are talking about shared electrons, then we are talking about a covalent bond. That's the first thing. And the prefix co means together. If you have a job, your co-worker works with you, right? So covalent bond, co equals together. They work together. In this case, literally their valences are together. So that means a hydrogen bond is out and the ionic bond is out. Neither of those things are going to happen. Now, if we are equally sharing, it's going to be either polar or nonpolar. Polar bonds, you have to think like poles, like a north pole and a south pole of a magnet, or the north pole and the south pole of Earth. It means opposites. You are going to get opposites when your electrons are not shared equally. They are going to be pulled a little bit more this way or a little bit more that way, in that some part of this bond or some part of this molecule is going to be a little bit more positive than the other part. In that case, they're not shared equally. They are shared unequally. So if we are equally sharing between two atoms, that would have to be a non-polar bond. They are sharing totally equally so that no one is winning the tug of war over the shared electrons, so there's no formation of a positive or a negative. So again, that was just a definition. If you can secure the first 30 questions, you are in good shape. Okay, so that was the first 10. We have 75 left. Ugh, this is going to take a while. I'm doing a few more of these also. So if you're watching the replay, make sure to subscribe so that you don't miss the next ones. I don't know exactly when I'm doing them, but they'll like show up in your feed as like a plans to go live at this time. And we're probably just going to do like the next 3 exams back. This one was good, so why not do the most recent one? I love question 11. Okay. Which statement describes the changes in bonding and energy that occur when a molecule of iodine, and they tell you the formula, I2, forms 2 separate atoms of iodine? So in this case, we have I2 breaking apart and becoming an iodine and another iodine. Okay, you wouldn't normally write it that way, but I just want to be able to show you what it kind of looks like. Okay, this one is barf. If your teacher never taught you this, your teacher is a party pooper. And you can tell them I said that. Barf. Barf stands for break a bond, absorb energy. Release energy when a bond is formed. Break, absorb, release, form. Okay. So, are we breaking or forming bonds? That's the first thing. We have 2 iodines breaking apart, right? They're bonded together. They're I2, and then they break apart. This is also a vocabulary question because molecules are bonded. There's a bond in a molecule. In atoms, there are no bonds. It's just like a little gold or a little iodine floating through space, okay? Molecules have bonds. Iodine is a molecule because it's one iodine bonded to another. So the molecule has a bond and the atoms do not. So when you go from molecule to atom, you have to break bonds. So in this case, we will be breaking bonds, which means we are going to be absorbing energy. So a bond is formed. No, we're not forming bonds. We are not forming bonds. Okay. A bond is broken. That's what we're doing, right? We're taking I2 and breaking it apart. And it is going to form 2 separate atoms of iodine. Break, absorb. We're looking to absorb energy, not release it. So this one would be choice 3. Okay. Next up. Question 12. The degree of polarity in the bond between a hydrogen atom and an oxygen atom in a molecule of water can be assessed using the difference in blank. Okay, here's another acronym. You ready? I love the acronyms. I'm a big fan of the acronyms. In this case, we are going to use the acronym BEND. Okay, BEND stands for bond electronegativity difference. And that will tell you if a bond is polar or nonpolar. So if you have fluorine bonded to fluorine, each with an electronegativity value of 4, You can look that up on table S. A 4 and a 4 in a tug of war, nobody wins. But if you have hydrogen and fluorine, which is a 4 and a 2.4 or 2.2, look it up on table S. Obviously the 4 is bigger than the 2 point something, so in that case you will have a whoosh, tug of war, right? You can subtract those two numbers to figure out if your bond is polar or nonpolar. You can also do it to figure out if your bond is ionic or covalent, but nobody really does that because you can just do metal, nonmetal, and that's quicker than having to plug it in to the little formula, right? So the difference in density has nothing to do with bond. Different in melting point has nothing to do with polarity of a bond. Intermolecular force is kind of the question. The degree of polarity will tell you what type of intermolecular force. So if you have a polar bond, then you would have a dipole-dipole force, right? You have a positive and a negative, and it'll talk to another molecule, the positive and negative. And they'll kind of like orient themselves in space that way. If they are nonpolar, then you'll just have that like electron cloud distortion. So you'll just have a dispersion force. So choice 4 is kind of like asking, it's the same as the question. Really what we want is the difference in electronegativities, and that is bond electronegativity difference. Okay. Whoop. Question 13. Which substance cannot be broken down by a chemical change? I don't know who wrote this test because this is kind of the same as, what was it, question 10? No. Question 8. It's kind of the same thing. This says which substance contains elements chemically combined in fixed proportion. That's the definition of a compound. Right here we have the definition of an element. A substance that cannot be broken down by a chemical change, by definition, would be an element. So it's really asking you which of these things is an element. And elements are found on the periodic table of elements. So that's all you'd have to do. Ammonia, you probably know the formula at this point, just from being a chemistry student, but the formula for ammonia is NH3. Water, everybody knows, is H2O. And then ethanol is an organic alcohol, which you know by that OL at the end. And it will have C2H1, 2, 3, 4, 5 with the OH group. Okay, so that's ethanol, made of carbon, hydrogen, and oxygen. Even if you didn't know the formula, you would know, hey, that's not an element because it's got multiple things in there. And krypton is Kr. It's the only one that's an element. Okay, 14. Which sample of matter is a mixture? Again, another classification of matter question. I like this test a lot. This one I'm finding is not too difficult so far. Although I'm sure in 25 questions I'll be like, this test is hard, I don't like it. Okay, CO2. That is a compound. If it is a compound, it itself is not a mixture. It could be part of a mixture, but it is not a mixture on its own. So that's a compound. Carbon tetrachloride, also a compound. Tin, SN, is an element. How do I know this? Okay. This only has one capital letter. One capital letter means that it's an element. Multiple capital letters means that you are at least looking at a compound, but it may be a mixture. Mixtures a lot of the time are going to have an and or a plus, but we have this right here. AQ. That little AQ. It stands for the term aqueous. Although some teachers are going to pronounce it aqueous. Okay? Aqueous, doesn't matter. It means dissolved in water, or at least mixed with water. You could have aqueous sand, I guess. That doesn't mix, it doesn't dissolve in water, but it would be like in a beaker of water, okay? That magnesium chloride is a compound that has been mixed with water. Hence that little AQ, or aqueous, is a mixture. Okay. Take a stretch break. My back and neck are very, very stiff these days. Okay. Need to do some stretches. Okay, question 15. Reference table question. Which term is used to express the concentration of an aqueous solution? Do you know which reference table it is? It's table D. Excuse me. Okay, table D. Oh, hiccups. I've had hiccups all day. This right here. It tells you in the table what each of these things measures. Okay, so parts per million is the answer. It is right here. Parts per million measures concentration of a solution. Concentration really just means how much stuff is in your other stuff. So there it is. Heat of fusion. Heat of fusion is not here because heat of fusion itself is not a measurement necessarily. It's the temperature at which you can get stuff to vaporize per gram, like how much energy you need, or not to vaporize, to freeze or melt. How much heat you need for something to freeze or melt based on its mass. It's not like it's a standard or like a physical constant. It itself is not like a measurement of like 12 inches or 14 grams. Okay. Pressure at 0 degrees Celsius and volume at 0 degrees Celsius are just pressure and volume at specific temperatures. That's like a very silly answer choice. I would have put in like mole or liters. I wouldn't have put in those answer choices. I don't know who wrote that. Okay, well, that's that. It's just parts per million. You look it up. The other ways to measure concentration are molarity, which is the number of moles you have per liter of solution. Then you have percent by volume, which is kind of the same as percent by mass. But you can also do concentration as percent by mass. That works as well. Okay. Next up, which particles, or rather the particles in which sample, have the lowest average kinetic energy? And for that one, we are looking at temperature. Temperature only. Thermal energy is based on the mass, but average kinetic energy is not. It's just temperature. So the question is, which of these samples has the lowest temperature? And that's it. That is it. The lowest number here is choice 1. 50 grams of sulfur has a temperature of 273 Kelvin. That is 0 Celsius. So if we have water in this situation, that water is freezing. 298, 300, 303, that's right around room temperature. And 323 is hot. Okay, 17. Which process represents a chemical change? Chemical change means that you have to break and form bonds. I guess you could do one or the other. In order to have a chemical change, you have to break or form bonds, which means that it cannot be a phase change. So iodine sublimes. Sublimes really means sublimation. That is going from solid, skipping over liquid, and going straight to gas. So because that's a phase change, it is not a chemical change. Water evaporating, we know, is going from liquid to gas. That, again, is a phase change. It's out. An ice cube melting is going from solid to liquid. Anybody else have to, like, think very hard about melting? I don't know why. And then a candle burns in air. Okay, burning. That's a pretty good indication where you're talking about a chemical change. But another Sesame Street question here. Which one of these is not like the others? You have 3 phase changes and then a candle burning. Not really a phase change. It kind of will look like a phase change, though. The candle is kind of trippy because if you've ever burned a candle before, you know that you go from a solid wax candle to this liquid wax candle. I get it. That's a side effect. Really, the candle burning is the wick inside. The wax just kind of like slows it down a little bit. Okay. Which equation represents a physical equilibrium? Ooh, that is an excellent question. Okay. Choice 3 is out immediately, simply because it doesn't have the double-sided arrow, and you're breaking and forming bonds. You're going from oxygen to ozone, so this one is going to be out. I don't like this question. I don't like this question at all. Oh, I really don't like this question. Any chemistry teachers here listening to this? I do not like this question. So a physical equilibrium, I would think that that would be a phase equilibrium. So like choice 4, right? You have liquid nitrogen becoming nitrogen gas and nitrogen gas becoming liquid nitrogen. And that double-sided arrow is indicating that we're in equilibrium, right? So I'm going to assume that that's the answer choice that they want. I'm going to assume that they want choice 4. Choice 3 and 2 are really the same situation. Those are chemical equilibriums. And I know this because I'm breaking and forming bonds. SO2 is combining with oxygen to give me SO3. In that, I'm breaking bonds. I'm breaking the bonds of the oxygen and adding them to the SO2 to give me SO3. That is definitely a chemical equilibrium. We have a chemical reaction happening there. Now, number 1 could be a physical equilibrium. It could be a solution equilibrium specifically. If you have a glass of water and you have a bunch of junk sitting on the bottom of the glass, what's going to happen is that the junk from the bottom is going to dissolve slowly. It's going to join the solution. But at the exact same moment, stuff that's in the solution is going to precipitate, meaning it's going to become a solid and sink down to the bottom. And that's going to happen in a loop. So something is going to dissolve and another thing is going to undissolve, and they're going to just like swap places, okay? I would want this question to be worded, which equation must represent a physical equilibrium? Because in choice 1, if it is not a saturated solution, the undissolving and the stuff dissolving from the bottom won't happen, okay? So in a saturated solution, meaning that there's stuff sitting on the bottom, there's not enough room in the solution for it to dissolve, or it's too cold for it to dissolve, you won't have an equilibrium because everything, well, if it's unsaturated, stuff will dissolve. So there won't be any stuff on the bottom. I want to see what they think. It better be choice 4. My guess also is that a lot of teachers contested this question. Let's see, what question was that? That was 18? Oh, where's the multiple choice answers? Now I have to go find it. That's not cool. Okay, I'm super curious about this. I'm going to pull a tab over. Let's see if I can find what they say. Do they not even have a key online? They have an answer booklet. They have a rating guide and a conversion chart. Interesting. Why is the stuff not here? Usually they have the multiple choice answers. Naughty, naughty. New York, what are you doing? That better be choice 4. If it's not choice 4, I'm going to be very upset. See, the other tests have scoring key and rating guide. They hit it. Got it. Boop-a-doop-a-doop. Let's see, let's see. How do I zoom in? How is anybody supposed to read this? Okay, let's download it. Question number 18 is choice 4. Choice 4. There we go. See? 18 is choice 4. I'm telling you, New York State is lucky that I don't teach there anymore because I would be on them like lightning reading that question. That is, I don't like this question. It's choice 4. It should say, which equation must represent a physical equilibrium? Because if you had a saturated solution, it would be in a solution equilibrium, which is a physical equilibrium because there's no bonds changing. Okay. Question 19 is a vocabulary question. Systems in nature tend to undergo changes toward. Okay. This is just energy and entropy. Okay. You are a part of nature. So this is the Netflix versus a marathon. What would you rather do? Would you rather spend a day running 26 miles or would you rather spend a day watching 26 Netflix episodes? I would pick Netflix 100 times out of 90 because I will never run a marathon. That does not sound fun. And that's because I am a part of nature. Nature likes a low energy state and a high entropy state. So low energy means we're watching Netflix and we are not cleaning our room. No. It's just messy. Entropy is a measure of disorder. So we would be picking choice 3 here. Oh my goodness, the hiccups today. Low energy, high entropy. You don't want to clean your room. So your room gets messy. Your room is messy because you won't clean it. Done. Okay, question 20. Which represents a hydrocarbon? I already know the answer to this. I'm thinking this question's harder than it is. Hydrocarbon means it only contains hydrogen and carbon. Hydrogen and carbon. Question 3. Contains chlorine. Choice 4. Contains oxygen. Choice 2. Contains oxygen. Choice 1 only contains carbon and hydrogen. Done. Whoop. Let me make sure we're still... Okay, we're still running here. Alrighty. 21. Which statement describes the bonding in an alkyne molecule? An alkyne molecule. I know alkynes contain triple bonds. Which is literally the answer choices. Okay. It's a definition. There has to be at least one carbon-to-carbon triple bond. Double bonds would be alkenes. A carbon-to-carbon triple bond would be the alkyne. The carbon-to-carbon single bond, well, I mean, a carbon-to-carbon single bond, that's not even true, because an alkyne would have at least one carbon. Oh, carbon-to-oxygen single bond. That's something with a functional group. That could be an alcohol. That could be an organic acid. That could be an ether. The list goes on. A carbon-to-oxygen double bond would be an aldehyde. Could be a ketone. Could be an organic acid. There's a few other things. Ester. It goes on. We could look this up. Let's see. Where's the reference table? Where'd it go? Nope. 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 It's right here. Duh. Okay. On table Q, alkynes right here. That right there is your triple bond. Now notice none of these have oxygen here. This is hydrocarbons, hydrogen and carbon. All of the pictures are just hydrogen and carbon. All the formulas are just hydrogen and carbon. Then the functional groups here, we have the single bonded oxygen, double bonded oxygen, double bonded oxygen, double bonded oxygen, single bonded oxygen. Double bonded and single bonded on the ester. Amides even have the double bonded oxygen. So you just look this one up. Again, we want to make sure that we rock the house on the first 30. Okay, we need the reference tables again for 22. Where'd it go? Question 22. Which compound has a functional group that contains 2 oxygen atoms? Gross. Okay, can we do this without drawing them? I'm sure we can, because it is a part A. If a part A question is taking you more than 45 seconds, you're probably doing it wrong. Just be aware of that. They are meant to be quick. Okay. Propanamine. Propanamine would be an amine. Guess what? That's the one that they gave you right here. They are goobers for choosing this as the answer choice. And that's good in your favor. Propanamine has 0 oxygens. So, not propanamine. 2-chloropropane. That would be a halocarbon, meaning that you have... Are they kidding? Wow. Okay, 2-chloropropane is also the one from the reference table. This question could have been super difficult. If this were a part B, then you probably would have to draw them and figure it out. But this one you don't have to, because it's literally in the reference tables. 2-chloropropane has 0 oxygens also, so that can't be your choice. Then we have methylpropanoate, which is this one right here. Yo, why is this ridiculous? Okay, methylpropanoate. You have the oxygen here, and then you have an oxygen right there. And all we're looking for is 2 oxygens. So I want to mark this as the answer, but I also want to check on the methyl ethyl ether, which, if you look here, only has 1 oxygen. So there we have it. Just look it up. Rock and roll. Okay. 23. Which term identifies a type of organic reaction? This one is always going to be like the process of elimination. Unless you know right off the bat. So deposition is the opposite of sublimation. Deposition is when you have a gas that is going to convert into a solid. And that is frost. When you have dampness in the air and it's cold enough and it touches a cold surface, instead of condensation like in the summertime, it's going to basically freeze. But because it's skipped over liquid, we don't call it freezing, we call it deposition. Distillation is a way to separate mixtures. Specifically, that's how you are going to separate homogeneous liquids by their boiling point. Oh my goodness. Cami is not my favorite app. Let's just say that. Okay. Then we have a polymerization. If you did a polymerization lab, you probably made slime. That's where you take tiny carbon molecules and link them together. And then vaporization is when you go from liquid to vapor. Some would also call that boiling. So again, it's really, in this case, they are asking you to know the definitions of each of those answer choices. That's what it is. you might need chemistry flashcards. Honestly, in order to prepare for the test, at this point, you should just be taking Regents exams. And if you're not taking Regents exams, then you should be reading, like literally open whatever book you have and read your glossary. Go over any vocabulary assignments that your teacher gave you throughout the year and just review the reference tables. Not that you need to know, like, I have memorized that it's halide, alcohol, ether. That's silly. It's just knowing what to look for, because you have like 12 pages of reference tables. It's kind of overwhelming. So if you can like really get to know your reference tables and learn to love them, then questions like 22 are going to be a lot easier, because you're like, oh yeah, that's on the reference table. I just have to look it up. Especially for the part A. Okay. 24 is an acronym. In an electrochemical cell, oxidation occurs at. Okay. You may have learned anox and the red cat. Anox is telling you that oxidation occurs at the anode. The red cat is telling you that reduction occurs at the cathode. Sorry about the keyboard. If it were up to me, it would not be this loud. It's not mine. So that's it. It's just memorizing. The salt bridge is for the migration of ions, to kind of like make sure that electrons continue going, like leaving the anode and going to the cathode. So, oxidation occurs at the anode. Oxidation is when you lose electrons. When electrons leave, the anode is going to become positive because of the lack of electrons, right? And if that anode is positive, the electrons are going to say, wait, that's positive, go back there. And they're not going to continue leaving the anode and going to the cathode. So that's what the salt bridge is for. The salt bridge helps to like flip the charges so that the electrons want to leave the anode and want to go to the cathode. That's what the salt bridge is for. Now that's only in a voltaic cell, sometimes called a galvanic cell. The switch is optional. It's not even important, really. It's just like whether the anode and the cathode are connected or not. They can only work if they're connected, but the switch is optional. Excuse me. Oh. So, oxidation is always going to be at the anode, regardless of the type of cell that we're talking about. Whether it's electrolytic or voltaic, oxidation occurs at the anode. Moving right along. Which energy conversion occurs in an operating electrolytic cell? So the electrolytic cell is the one that requires electricity. A lot of the time, the power source is a battery, but you could also plug it into the wall. Doesn't have to be a battery. For a while, we were telling kids it had to be a battery. I don't know why we were doing that, but it could just be any type of power source. So if we have a power source, that means that we are converting electrical energy into something else. When you, sorry about the dog. When you have electrical energy to run lights, you have electrical converting to light energy. If you are charging up a battery, you have electrical converting to chemical. Because the electrochemical, or rather the electrolytic cell, is going to be used to have a chemical reaction take place, whether that is electroplating or perhaps it is electrolysis, where you break something down. A lot of the time we just do it with water. We take water, run an electrical charge through it, and then it breaks apart into hydrogen and oxygen. That's electrolysis. That's chemical energy that we're forming there. So that's what it is. Okay. I don't know why the Regents exam does this. They must not have like the rights to say Bronsted-Lowry. 26, they're talking about Bronsted-Lowry acid base. The one acid base theory. I don't know why they just don't say it. It's saying one acid base theory states that a base is an H- donor, an H- acceptor, an H+ donor, or an H+ acceptor. Well, guess what? There's no such thing as H-. It literally does not exist. Hydrogen has one proton, and if you took that proton away, it would just be an electron. And there would be no proton to identify the fact that it was hydrogen. It would just be an electron. So those literally just don't exist. And then we get into H+. Oh. Excuse me. The H+ donor or the H+ acceptor. And with that, we are going to rely on the acronym. Another acronym. This acronym is BAD. BAD stands for bases accept and acids donate. Okay. And that is referring to protons or H+ or hydrogen ion. All of those terms right there are interchangeable. Bases accept protons and acids donate them. So that's just what Bronson-Lowry said. It is an H+ acceptor. The reason we had to do this was because ammonia, NH3, you dissolve in water, it becomes NH4. It has basic properties. It is a high pH, so higher than 7, meaning that it's a base. It has like a slippery feel like a base does. And he put 2 and 2 together that it is because of the accepting of hydrogens. That hydrogen, the hydrogen it is accepting is coming from water. So the OH that appears is the leftovers of water. So I'm going to do it for you right here. We have NH3. We are going to dissolve it in water. And what's going to happen is that the NH3 is going to take one of water's protons, one of water's hydrogen ions, and then it is going to have the OH, which is the leftover of water. You can kind of see it better if I write water like HOH. This OH right here is this one right there, and then that H gets embedded into the NH3 and it becomes NH4. So really the difference here is that the hydroxide, that OH, doesn't come from the base itself. It forces water to kind of act like the base. Okay. Moving on to 27. The acidity or alkalinity of a solution can be measured by its... I don't think that's on table F. B, D. No, it's not. So you'd have to know the definition. Look at that. Okay, well, boiling point and freezing point is not going to tell you whether something is an acid or base. The electronegativity value, we already answered a question on that said that it was going to be used to tell us if something was polar or nonpolar, or what type of bond we're looking at, ionic or covalent. So it would have to be the pH value. Again, this is just a definition question. It's asking you, do you know the definition of a pH? I know that it is not the most fun question, these definitions, but that's what they do. They love asking definition questions. Okay. Just a few more in part A. Let's see what we got. The nucleus of an atom of neon-19 decays. Which particle is emitted? That's a reference table question. And this is why you want to know the reference tables, because otherwise you're like, what the heck? How do I even answer this? Well, darling, you answer with a reference table question. Neon-19. Wait, what? Why? Oh, it's right here. I'm thinking I'm using an outdated reference table and they switched it up on me. No, neon-19. It is emitting this particle B+. And then you're like, what the heck is B+? Well, B+, you could look at the next table. B plus is this right here. B plus is called a positron. The other symbol for B plus is that right there, which we would come over here is choice 4. That is called a positron. More reference table questions. Which nuclear emission has the greatest mass? Guess what? We're back to this table O. So wait, this was which one? N? This was a combination of N and O. And this one is just O. Which one has the greatest mass? Okay. Gamma rays are gamma radiation, same thing. The 0, 0 indicates that we have no mass and no charge. The positron is what we just answered. That 0 on top tells us that we have no measurable mass, same as the electron. It does exist, but we don't typically write it because it's so tiny. Beta particle is the negative version of the positron. And again, we have that 0, so it has no measured mass based on like significant figures. And then that alpha particle has a 4 on the top. It has the greatest mass. Okay, then we have question 30. Which statement describes the net change that occurs during nuclear fission? Okay, during nuclear fission. Okay. Electrons don't convert to protons and protons don't convert to electrons. At least not in high school chemistry class. That doesn't happen. Nuclear fission is the one where you have like a big uranium, thorium, plutonium, something huge. You got over 200 particles in the nucleus, and you're gonna hit it with a little something, and then it's gonna blow up, okay? When we do that in a controlled way, we get nuclear power. When we do that in a mostly uncontrolled way, you're gonna get a nuclear bomb, okay? The reason that nuclear power and nuclear warheads are so good at what they do, put that in quotes, is because you can get a heck of a lot of energy out of a small amount of matter. So, we have energy, mass rather, is converted to energy. If you have like a can of uranium, it can like power a city. I don't know what the actual numbers are, but it's a heck of a lot of energy compared to the amount of matter. If you wanted to burn coal, you have to burn a lot of coal. You have to burn a lot. Same with like oil. When you have a chemical reaction, the amount of energy that you get is going to be comparable to the amount of energy is going to be comparable to the amount of matter that goes in. But when it's nuclear, it is a huge disparity. Okay, so that's everything on part A. We have been at this for an hour 15, which you should be able to cut that amount of time like really in half. Because you're not going over every single answer choice as if you were teaching a bunch of students. Okay. Moving right along. Part B. This is where we're going to start using a calculator. I am using just a TI-30 basic. Scientific calculators are all you are allowed to have. The most that you should need to do is like maybe squaring something. You can mostly get away with a 4 function if you have to bring your own calculator. We'll see what happens here. Okay. Here we go. What is the net charge of a monatomic ion that contains 15 protons, 16 neutrons, and 18 electrons? This, honestly, is a very easy question. It's only here because it requires, like, 2-step thinking. That's what a Part B question is that you have to, like, think of one thing and then probably apply it to think of something else to get the answer. So in this case, we are talking about a monatomic ion, so not a poly, okay? So this would be something like a fluorine ion, or a chlorine ion, or a magnesium ion, right? And it would be like a -1. You could have a magnesium ion that's a +2. We're talking about just one atom making an ion. And in this case, our ion has 15 protons. Real quick, I'm going to look at my periodic table. I got a pocket-sized one. And it has a little mole on it. Isn't he cute? And it's got another mole right there. American Chemical Society, baby. Okay. If I have 15 protons, I would be working with an atom of phosphorus. And I know that because phosphorus is number 15 on the periodic table, okay? And if I have 15 protons, that is 15 positives. Neutrons don't have a charge, they are neutral, and electrons are negative, but I have 18 of them. So in this case, you could sit here and do the math. 18 is 3 more than 5, and electrons are negative. So my charge is going to wind up being -3, because electrons are negative. Okay. I want to go over these, but I don't want to spend a crazy amount of time going over things that are probably easy. I'd rather just like skip to the good stuff. Okay. 32 says the table below shows the atomic masses and natural abundances of 2 naturally occurring isotopes of rhenium. Okay. The question, which numerical setup can be used to calculate the atomic mass of rhenium? Okay. There's 2 options here. Number 1, you could know how to set it up. Or number 2, sit and calculate it and then compare it to the periodic table. So that's 2 ways to get the answer. The correct way to do this would be to take the atomic mass of the first isotope. It is not time for anything. Did you just hear him crying? He's such a baby. You take the atomic mass and you would multiply it by the percent abundance, but the percent abundance here is reported as a percent. So you would have to either divide this by 100 or move the decimal 2 places to the left to put the decimal out front. It's kind of like percent is almost like a unit, okay? And you have to get it out of that unit to be a functional number. Because percent really means 37.40 divided by 100. That's really what 37.40% means. So you're kind of like in the middle of a calculation when you report that number. So we would take choice 2 here. We have the atomic mass, 184.95, and we're multiplying it by the percent abundance, which has already been divided by 100. And then we are going to add that to the next isotope and its mass, multiplied by its percent abundance, already divided by 100. These 2 choices, dividing by 2, is not going to give you a weighted average, necessarily. They're just wrong. And then that first one, the whole thing would have to be divided by 100. Actually, no. Actually, yes. Because you got to get the percentages out of percentages. Okay. Let's keep going. Okay, periodic table trends. Which general trend is observed as the elements in period 2 are considered from left to right? Okay. A few of these you could just look up on the periodic, or rather on table S. You don't have to look them up. I mean, you don't have to look them up. You could just know the trends, but I maybe would look them up. I don't know. Shrink this, move this way. Ooh. I'm on my husband's computer. That's why there's aliens on the screen. Okay. Which general trend is observed as the elements in period 2 are considered from left to right? If we look at the elements in period 2, we would be beginning with lithium. Remember, the periods go side to side. And they tell you that right here. These are the periods. 1, 2, 3, 4, 5, 6, 7. This here is also period 6. This is 6 and this is 7. They repeat. Okay? Because they really belong right here. They just cut them out and stuck them on the bottom to make more room because this thing does not print nicely. I realize I am not centered. Who was that bothering? I apologize. Okay, so atomic mass decreases. The atomic mass is at the tippy top here, 12.011. We have 6.9, 9.0, 10.8, 12, 14, 16, 19, and 20. So that's not happening. Atomic mass is increasing. Melting point increases. Okay. Lithium, beryllium, boron, carbon, those are solids. And then nitrogen, oxygen, fluorine, and neon are all gases. So the melting point is not going to the melting point is increasing. Right? Electronegativity is definitely the answer. Fluorine has the highest electronegativity at 4.0. Oxygen's like 3.2. Maybe 3.4. Nitrogen's 3 point something. Carbon is 2.4. Electronegativity is definitely increasing. First ionization energy is the amount of energy it takes to remove an electron and make a positive ion. Lithium loves being a positive ion, so it is a very low ionization energy. Meanwhile, fluorine has a very high ionization energy because it doesn't want to be a positive ion. It takes a lot of energy to remove its electron. So the first ionization energy is increasing a lot. Now I'm curious about this melting point. Melting point increases. Okay, melting point for lithium in Kelvin. I don't know where my brain was right there. Because it's 454, 1560, 2348. So it does increase, but then it drops a lot. I don't know why there's no melting point for carbon. Probably because there's too many allotropes. Like, whether it's carbon, like graphite, or carbon diamond. Because you have to, it's a lot to melt diamond. And I guess coal doesn't really melt, it just burns. So that makes sense. And then these are melting at 63, 54. Yeah, I don't know why my brain was just thinking that. There you have it. Excuse me. Okay, other periodic table trends. Fluorine has the highest electronegativity. It has the highest first ionization energy. It has the smallest radius. It has the least metallic character. I think that's it. Francium is the opposites. So if you consider the two corners of the periodic table, francium and fluorine, and then you look at them and you consider their corners like dictating the trends, you'll be good. I'm not going to go into it too much. Go find the video on periodic table trends on this channel. It'll be good. Okay. Which formula represents chromium-3 oxide? Chromium-3 oxide is telling you that chromium has a +3 charge. Oxygen will always have a -2 charge. Notice on the periodic table over yonder, it has only a -2. So when you crisscross this, this 3 would come over here, and this 2 comes over here, and you would be left with Cr2O3 as the chemical formula for chromium-3 oxide. This one would be chromium-6 oxide. This one never happens, and this one never happens. Those indicate that oxygen has a 3 for the charge. Not happening. This could happen. What this would be is chromium with a +6, crisscrossing with an oxygen with a -2. Crisscross them, you would get Cr2O6. Each of these is divisible by 2. Remember, we have to simplify the subscripts for ionic compounds. So if you divide 2 by 2, you get 1 with the invisible 1. And chromium, or rather the oxygen, instead of having 6 of them, you'd have 3 of them. So that would be chromium 6 oxide. Okay, for question 35, given the balance equation representing a reaction, what is the mass of, ooh, I love this. Okay. What is the mass of potassium chloride produced when 24.51 grams of potassium chlorate reacts to produce 9.60 grams of oxygen? So if we are putting in 24.51 grams of reactant, we should get 24.51 grams of product. It's going to be split between all the products, but it's telling us that we are producing 9.60 grams of oxygen. To set this up like it's algebra. The energy doesn't count because it doesn't have any mass, so we can just kind of like ignore that for now. We have 24.51 is equal to, I don't know how much potassium chloride, plus 960. So you just subtract. 2451 is the total, and we're going to subtract the 960 that represents the oxygen, and 14.91 is the potassium chloride. That's what's left over. This is the law of conservation applied. The law of conservation states that matter, energy, and charge are all conserved in chemical reactions. So that's it. You really are just making sure that you put 24.51 in there, 24.51 has to come out. And if 9.60 is oxygen, the rest has to be the potassium chloride. It looks like it's a stoichiometry problem. It looks like it's hard, but it's not. It's a law of conservation question. Okay. 36. Which represents a conservation of atoms? That's really asking you which of these is balanced. So you have to go through and really just figure out if you have the same number of stuff on each side. So let's zoom in real quick. For choice 1, we have 1 titanium on each side, but we have 2 oxygens right here, and we have 6 oxygens over here. There's a fly in my house, and the dog is chasing it. He's been chasing it all day and just like trying to eat it. I think he's just freaking out right now. Okay, so then I have 2 aluminums on this side and 4 aluminums on this side, so that is not conserved. We have gained a bunch of oxygens, but lost a bunch of aluminums, so that's no good. Okay, second one. 1 titanium on each side. This one has 2 oxygens, but over here I have 6. So that is no good. We don't even have to look at aluminum. Next up, I have 3 titaniums and 3 titaniums. Okay. 6 oxygens. 3 times 2 is 6. 2 times 3 is 6. Hey, cut it out. And here I have 2 aluminums, but here I have 4, so that's not going to be any good. Excuse me. Sir. No scratching the floor, please. Thank you. Okay, for the last one, we have 3 titaniums in the reactants, 3 titaniums in the products. This 3 times the 2 is going to give me 6 oxygens. The 2, big 2 times little 3 is going to give me 6 oxygens. And then I have 4 aluminums. And this 2 times that 2 is going to give me another 4 aluminums. So, option 4 is balanced. I like these because if you're not great at balancing equations, you have 4 choices to decide which one is balanced. So you don't actually have to do like a lot on your own. Okay. This one, I love this one for you. If I were writing this question, I would not put the formula in here. The Regents board was very nice to you by doing that. It says 1 mole of bromine gas with the formula Br2 has a mass of blank. Now, Some of you are going to have to set up a ratio to do this. No, you don't. You set up a QMT chart, okay? QMT stands for quantity, mass, and total. And this is what I do to find a molar mass or a gram formula mass for some of you. So this is bromine, so it's kind of easy, but you could also do this for like really big formulas that are really ugly. You list all your elements. Q stands for quantity. We have 2 bromines. The mass is just the mass that you pull from the periodic table. And then that would be 79.90. And then the total you multiply going across. So it's just 7990 times 2. Some of us don't need to do the chart. Some of us do. 159.8 is going to represent the 2 bromines. That's it. A mole is the amount of stuff on the periodic table. Okay, so there you have that. Oop, and I love this because it's just a definition. Given the equation representing a reaction, 2 sodium chlorides become 2 sodiums and 1 diatomic chlorine. That is a decomposition reaction. Okay, the double replacement is when you have them swapping partners. So you would have A, B, and C, D, and they're going to swap. So if you remember, we always put the positive thing first, right? A is positive. It does not want to be with the positive C. It doesn't want to be with negative B because then there's no reaction happening. So it is going to pair up with negative D, and we're going to make a D. And then, can this go away? And then we have a positive C, which is going to pair up with negative B, and we're going to make CB, okay? The positive thing in chemical formulas is always going to come first. So that is that. Decomposition is when we break stuff down into smaller pieces. Synthesis would be the opposite of that, where you take 2 small things and kind of squeeze them together to make something bigger. And then the single replacement is the Steele reaction. So you would have something like A, B, and it's going to try to make a bond with C. And if C is a positive thing, then you would have CB plus A. If C is a negative thing, then you would have AC plus B. Either way, what's happening here is that C is the single element who comes in and kind of steals an ion from the other compound that is trying to steal from. Okay? So for 38, this is a decomposition because the sodium chloride breaks down into sodium and chlorine. A lot of the time, our decomps are actually going to break down into their elements. Not all the time, but it does happen. Okay. Electrolysis, a lot of the time, is also a decomp. Ooh, okay, 39. Another good one, because 39 is a acronym question. Okay, the acronym. Which statement describes the charge and radius of a magnesium ion formed when magnesium loses 2 electrons? Okay, this reaction, or rather this acronym, comes from my high school chemistry teacher. So you're not allowed to make fun of it because she's a very nice lady. It is MELPS. Okay, MELPS stands for metals, electrons lose, positive smaller. And the way you remember it is that MELPS helps. Okay, metals, magnesium is a metal. So when the metal loses electrons, which they told you in this question because they were very nice to give you this information. Whoop. It's going to lose 2 electrons. So it is losing electrons, right? Now it is going to become a positive ion. Because remember, electrons are negative. So if you kick negative people out of your life is going to become more positive. Same thing for magnesium. If it ditches electrons, it is going to become more positive. Now, when it does that, it is going to become smaller. And the reason is because magnesium is losing its valence shell. Okay, so magnesium is in period 3 of the periodic table, which tells me that we have our 12 protons right here. I'm just going to draw it like half sized. Okay, 1, 2, 3. Okay, and we have 2 electrons in this valence shell. We've got 8 right there, and we have 2 right there. Okay, if magnesium ditches those 2 electrons, then this entire shell is just gone. Okay, I'm going to try to erase it with white because I don't know how to erase in Cami. Okay, so this is going to be gone because it got rid of these 2 electrons. Boom. And now it's smaller. The opposite is true for the nonmetals. The nonmetals gain electrons, and because they have some added electron repulsions, they're going to like pop open a little bit. And they're also going to gain electrons and become negative. So MELPS helps not just with metals, but it also helps with nonmetals, because if you know the reverse, then you're good. Okay? So magnesium is going to be a positive ion, and the radius is going to be smaller. So, oh, I need to have a sneeze. Magnesium ion is positive, radius is larger. No. Magnesium ion is negative. No. Magnesium is positive. Excuse me. And the radius is smaller. So that is our answer. 39 is 3, choice 3. Okay. Moving on to 40. An oxide ion, O2, or rather O minus 2, or 2 minus, has the same electron configuration as an atom of which noble gas? Okay. I love these questions. Oxide ion is O2 with a, or O with a minus 2 charge. Okay. This means that it has gained 2 electrons. How do I know it gained 2 electrons? Because electrons are negative. And if you take on a bunch of negatives, you're going to become negative. If you have negative people in your life is just going to be cranky and miserable. Not fun. So, if we take a look at the reference table and we take a look at oxygen over here, if oxygen gains 2 electrons, right? Oxygen originally has 8 electrons, fluorine has 9 electrons, and neon has 10 electrons, right? So if oxygen gains 1 and then 2 electrons, it's going to look like neon. And that's it. It's just got 10 electrons. So does neon. And once oxygen has those 2 electrons, or those 2 extra electrons, and it looks like neon, it's like, I'm cool. I'm like a noble gas. Noble means like kings and queens. So that's a really good one to look like. Okay. 41. What is the vapor pressure of propanone at 45 Celsius? And then you ask yourself, how the heck am I supposed to know that? And you're like, oh yeah, I have a reference table. That's how. Okay. We are going to look for the reference table on vapor pressure, which is the one with the 4 lines on the graph, which I believe is H. Yes. Okay. The big thing here is to make sure that you are looking at the correct line. Because I guarantee you the wrong answers are correct for the other substances. Okay. So we are looking at the line for propanone, which is this first line here. We want the vapor pressure at 45 Celsius. Oh, you know why I don't like this table? Because on the y-axis, it goes by tens. And on the x-axis, it goes by fives. Okay? So this is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. If I were going to have to read this table for a test, I would go in and like fill all of these in, honestly. You can write on the reference table that they give you for the test. They have to give you a fresh, clean one. On the x-axis here, it goes by fives. That's 5, 10, 15, 20, 25 is written, 30, 35, 40. Okay. We need propanone at 45 Celsius, which is this line that I just quit at. Knucklehead. Okay, and we're going to slide up until we hit propanone, which, if I could write on this tablet, comes out right there. All right, and then we're going to slide over to what the vapor pressure is. And we are getting 70 kilopascals. I would not anticipate that they would change the units on you, but I would be careful. Because they could be very big meanies and just write pascals as the answer choice, even though this table is measuring in kilopascals. I've never seen it happen, but the Regents Board is not known to be nice to you. We looked at that rating table when we first started this stream. There are some times where your correct answers just don't matter. We looked at that other question that I didn't like the choices for. Just be careful, okay? I'm not anticipating it, but be careful. Because question 42 is a question that you need to be careful about. 42 literally tells you based on table G. So before you even continue, go look at table G. Table G is the worst table to ever exist because it looks like a circus. We have like 10 graphs on one graph. It's not a fun time, okay? Just do your best. Take a deep breath. You can write all over this. Table G, what is the mass of KCl that must be dissolved in 200 grams of water at 10 degrees Celsius to make it a saturated solution? Okay. Table G is based on dissolving stuff in 100 grams of water. This is why table G is not nice. We don't like table G all that much. KCl is right here. It's this line. There's not really a highlight function on this thing, okay? That's the line we're looking at. It asks, what must be dissolved at 10 degrees Celsius in 200 grams of water? So I want to kind of undo this. Maybe I want to redo it. We want to look at that. If you're allowed to bring a highlighter, I don't remember. I would bring one. This way you could just like highlight these lines on this table because there are some zones of this graph where it just gets very chaotic. Okay, at 10 degrees Celsius, I could dissolve 29 grams of KCl in 100 grams of water, right? This comes over right here. We're at the 30 grams, and here we're at 10 degrees Celsius. This graph is not so bad because each like line on this graph is the same size, okay? They're perfect squares. It's a 10 by 10. So the incorrect answer is 30. Reason being is that if you double the amount of water, you can double the amount of stuff that you can dissolve. So again, this table is based on dissolving. There's an eraser right here. How long did it take me to find that? Okay. This table is based on dissolving in 100 grams of water. If you double the amount of water, you can double the amount of stuff that you can dissolve. So it's not 30. 30 is what you can dissolve in 100 grams of water. 60 is what you could dissolve in 200 grams of water. Be careful though, because they also will cut this in half. They won't just do 200, they'll also do 50. That can be dissolved in 50 grams of water because it's 30 divided by 2, the same as 100 grams of water divided by 2 to get the 50. And 120 would be multiplying by 4. That would be in 400 grams of water. I would assume they would do an answer choice that's based on the wrong line. But that's that. Okay. So the correct answer here is the 3. You double the amount of water, you can double the amount of stuff that you can dissolve. 43, another great question. You know why? It tells you to go look at table I. H and I. Okay, table I. Again, kind of a hot mess. Based on table I, which chemical equation represents a reaction with a heat of reaction that indicates a net release of energy? Okay. This is easy. Ready? If we are releasing energy, that would mean that our reaction would have to be exothermic. Exothermic means heat exits. Endothermic means heat enters. There is a teeny tiny little note down here that you probably never noticed. Woo! That's not what I want. Get out of here. This little note right down here. A minus sign indicates an exothermic reaction. Girl, they told you that this was an exothermic reaction. They just want you to figure out which of these answer choices has a negative for that delta H value. And even if you don't know what a delta H value is, H, heat of reaction. This says heat of reaction, right? That's the title of the table. It's telling you based on table I. It tells you where to look. It gives you this little note down at the bottom. We know that we're looking for a negative sign. Now, the tough part of this is that you look at it and it kind of just looks like a blur, right? We are looking for N2 gas and O2 gas, making 2NO gas. That is this one right here. No, it's not. See, I just messed it up. It's this one right here. Positive 182. That's not what we want because we're looking for a negative because we want one that's releasing energy, letting energy out. The next one, N2N2O2 as a gas is giving us 2NO2. That is the one just beneath it. And again, that has a positive delta H, so we don't want that one. Next up, we want 2 carbons and 3 hydrogens making C2H6 gas. Oh, goodness gracious. That's this one right here, and look at that. That's got a negative. But you know what? Just for the sake of playing fair, let's look up the last one. I'm going to erase this a little bit right here. Oh, it just erased the whole thing, of course. Okay, we were looking at this one with the negative 84. Problem is that I just wrote over the next thing. Okay, and now we're here. 2 carbons and hydrogens making C2H4, and we're getting a positive 52, okay? All of the answer choices, this one was positive, this one's positive, and this one was positive. So we're going to choose choice 3 because it's the only one that has a negative delta H. Now, again, kind of a Sesame Street question. It's harder, obviously, because you have to do a lot more thinking for this one. But this, again, is which one of these is not like the others. You have 3 answers that come up with a positive delta H and one that has a negative delta H. Even if you weren't sure that exothermic meant releasing energy or that you didn't know that that little note was there, when you look it up and you get 3 of a kind versus 1 of a kind, pick the 1, not the 3. They do it a lot. It's happened 3 times here. Okay, question 4. The greatest increase in entropy occurs when a 1 gram sample of water changes from what to what? Okay, this is also going to be kind of sort of a which one of these is not like the others, okay? Entropy, remember, is disorder. There are a few ways to like increase entropy. So we're going to do like max entropy. Whoop. Max entropy is going to occur when you have a gas, when you have a hot sample, when you have a concentrated sample, when you have gas, it's hot, it's concentrated. Let's see. It takes up a large volume. It's not organized. Solid to liquid, obviously we're increasing entropy, and that's great. Okay, but we're only increasing it a little bit. Solid to gas, we're kind of doing two phase changes, right? We're skipping over liquid and we're going straight to gas. Gas to liquid, we're getting more organized, and liquid to solid, we are getting very organized. So I would say that the correct answer is going from solid to gas, just because solids have a definite volume and a definite shape, and gases don't have either of those because gases are compressible. So there's like a lot of chaos in a gas. The particles are always moving. They're in constant random straight line motion, right? Because of the kinetic molecular theory. They're all over the place, and you have a huge increase in entropy because they're going from like a very specific spot in an organized solid to just being all over the place. Okay. I really want to finish this in the next half hour because I have to feed the DOG. Okay, which particle diagram represents one substance only? Oh, this is easy. Okay, one substance only. This should have been a part A question. This is number 1. This is something diatomic. This could be hydrogen. This could be, I would assume it's hydrogen, just because of this 3 right here, I guess. I don't really know. It's not a mixture. Substances mean element or compound, because substances are pure, meaning that they have a definitive chemical formula. H2O is a pure substance because it's always H2O, but salt water is always going to be salt and water, but the amount is going to change, right? So that makes it not a pure substance or a substance. That makes it a mixture. Substance and mixtures are opposites. So it's a vocab question. It's reading particle diagrams. The rest of these are mixtures. This is 1 white, 1 black. This is 2 white, 1 black. This is just rogue atoms floating around. And this is diatomic, but this looks, I mean, two different types of diatomics. It looks a little too organized, though. Ooh, okay, 46 is telling us flat out use table J. Love it. I love when they tell us a table to pick, or a table to use. Based on table J, atoms of which metal will lose electrons to calcium? All right, we have calcium right here. This is kind of a Sesame Street question. Again, so we're taking calcium and we are going to compare it to aluminum and to nickel and to lead and to potassium. Okay, did you figure it out? They're not so bad, right? It is potassium. Okay, the things at the top of table J are very active, and that means that they make great anodes. They love to lose electrons. The things at the bottom or lower don't love to gain electrons, but they're willing to gain electrons because the metal that's up the list is forcing them to take electrons. So potassium, really what this means is that potassium has more metallic character than calcium does to some extent. Potassium is like really pushing to get rid of those electrons, and so is calcium, but potassium has a stronger ability to get rid of electrons, and calcium just kind of gets stuck taking them. If you think of any voltaic cell, even if it's just like a copper zinc voltaic cell, all metals want to lose electrons. Some of them are just better at it than others, and those are at the top of table J. Okay, 47, excellent question. Which aqueous solution is the best conductor of electrical current? All right. Oh, okay, this was really great. every single one of these answer choices is talking about sodium nitrate. Sodium nitrate is often what we talk about when we're doing like voltaic cells and electrolytes. And the reason for that is because based on table F, yes, sodium is a group 1 ion, always dissolves no matter what. Nitrate is a negative ion, loves to dissolve all the time no matter what. So pair them together. Those two love dissolving. So that's really great. I would assume that something here would have been insoluble, but all of our answer choices are the same compound. So really the question is asking about concentration, because that's what the capital M is, right? It's molarity. So we want to have the highest concentration, because when you have the higher concentration of salts, you have a lot of sodium +1 floating around, and you have a lot of nitrate -1 floating around, you are going to have a really good ability to conduct electricity. Now, electricity is just moving charge, basically. It's electrons moving around. And when you have a bunch of those positive ions floating around inside the solution, they're able to like kind of let the electrons swim through. Okay? So that's it. It's simply because it has the highest concentration. Now, a lot of the ways that they'll ask this is that they'll do something like sodium nitrate, but then they would also do like, what's another one that we could do? Let's say we did calcium. Could we do calcium? Calcium nitrate. Why not? That would be Ca2, and no, that's not right. CaNO3 2. Right? This one actually breaks into 3 ions, because you would have a calcium with a +2, and then you'd have nitrate twice. NO3 with a -1, and then you'd have another NO3 with a -1. And if you are able to compare stuff like that, then you're looking for the highest number of ions. Okay? So sometimes they even mix and match those. They'll have 2 answer choices of the same chemical, and then they'll also have different concentrations. So it'll be like these 2, right? And then they would do calcium nitrate with those same concentrations. So in order to get the best conductor for your electrolyte, you are going to have the highest concentration of stuff and the most ions. Be careful. The covalent stuff may have a ton of atoms, but they don't form ions, right? So if you dissolve sugar, it is not an electrolyte because the sugar molecule doesn't break apart into ions. Okay. Next, given the equation representing a reaction, the equation represents blank. Okay, I love this because choice 1 and 2 are not even chemical reactions. We've gone over this. Sublimation is going from solid, skipping over liquid and going straight to gas. Condensation is when you have a gas and it converts into a liquid. So if I had like ice in this glass and there was humidity, dampness in the air, and it kind of floats over and it touches the glass, and then it's going to be cold enough that it condenses, and then you got like a sweaty glass, right? That's condensation. Fission is when you have something big and it breaks apart in a giant nuclear reaction. So like uranium, plutonium, thorium, something very, very big. Fusion is when you have 2 small things like hydrogen, helium, and then they fuse together and make something bigger. That's the reaction that runs the sun. And that's what we're working with here. Hydrogens are fusing together and forming helium. Okay. Moving right along. Oh, I love this. Which formula represents 2-butene? If we go over to the organic stuff. Okay. This is a P and Q question. Butene is going to have 4 carbons, so we are looking for 4 carbons, and lucky for us, every single one of these has 4 carbons. Great, that didn't narrow anything down. This "ene" ending right here indicates that we are talking about some type of alkene, right? The alkene must have a double bond in it, so we are only looking for choices that have a double bond. That is a triple bond, so 3 is out, and that is a triple bond, so 4 is out. And then the question is, what is going on with this 2? 2-butene means that we have a double bond between carbon 2 and 3. I know that it's not between carbons 1 and 2, but instead between 2 and 3, because we always report the smaller number. Okay? So if our double bond were between carbons 1 and 2, we would call it 1-butene. 2-butene is going to, come on, move that thing. 2-butene is going to refer to a double bond between carbons 2 and 3. And remember, you have to count from both directions. You have to count from left to right and from right to left. And the reason is because this molecule, even though it's flat on paper, in real life, it is moving and spinning around, right? So if I'm looking at it this way, right, you're looking at it the opposite way. So you have to count from both directions to make sure that no matter which way you count, you're going to get it between carbons 2 and 3. So if I count this 1, 2, 3, and 4, and then I switch, and then I count it backwards, right? 1, 2, 3, and 4. The lowest number out of all of those is 1. So that would be 1-butene. And this right here has to be the 2-butene. But let's do it. We have 1, 2, 3, and 4. And it's, in this case, it's going to be the same, but it doesn't have to. 1, 2, 3, and 4. 2 is the lowest number. So this one is actually 2-butene, and that's how we know. Okay, next up, 50. We have this compound. Which formula represents an isomer of the compound? Okay, isomers, we spoke about this back when we were talking about allotropes. Isomers are the same stuff, all plucked apart and rearranged and built differently, okay? So we have to have in our isomer 3 carbons. All of these have 3 carbons. Actually, let's do this. Let's do the formula. 1, 2, 3 carbons. So this is going to be C3. Then we have H's. We have 3, 4, 5, 6, 7, 8. We have 8 oxygens. 8 hydrogens, and then just the 1 oxygen. I'm going to put the 1 there, just for the sake of counting it right now, okay? Now right here, I have C3, H, 1, 2, 3, 4, 5, 6, 7, 8, and 1 oxygen. Okay, I like that. Let's keep going. Choice 3, I have 3 carbons. That's great. I have 1, 2, 3, 4, 5, 6 hydrogens. I lost 2 hydrogens there. And I do have the 1 oxygen, which is good, but it's not right. So that's not it. Here, 1, 2, 3 carbons. 1, 2, 3, 4, 5, 6 hydrogens. Again, I lost those hydrogens. And then 1 oxygen. The reason here, truthfully, is the double bond. The double bond is like taking the place of a hydrogen. And that's what's throwing us off here. C3, H, 1, 2, 3, 4, 5, 6. Are you saying it? And then oxygen, and I have just 1 of those. So this is going to be choice 1. Really, this oxygen was like plucked off and then put in the middle of our carbon chain. Okay, so that is the first 50 questions. That is the multiple choice. If you need to pause, stretch, take a break, now is the time, because we are going to get into part C. No, B2. B2 are the simpler of the free response questions. I wish they were like C and D instead of B1 and B2, but whatever. Okay, so these are the ones that are going to require more thinking. Obviously, the test is getting harder as we go. These are kind of just like random thrown at you free response questions where part C is like a little blurb, a little story, and then you have to apply some stuff. I'm going to take my answer booklet over here. Okay, there's no context for these B2 questions a lot of the time. This first one has absolutely no context. Make sure you fill this out correctly. And make sure you sign the thing that says you didn't cheat, okay? Those always cause problems for teachers. Don't be that kid. Okay, so this first question asks, in terms of protons and neutrons, explain why P32 and P31 are different isotopes of phosphorus. Okay, this is a great question. I'm just trying to size this so that we're working nicely here. Okay, so for 51, P32 and P31, we have to talk about it in terms of protons and neutrons, which means your answer must include the word proton and must include the word neutron. You have to have that or it's not going to be marked correct. Okay, P32 and P31 have the same number of protons, but a different number of neutrons. You can underline those terms when you answer the question, if you like. Whoever's grading it might appreciate that. But it helps you to know, like, hey, I definitely answered this question the way that they asked. That is the definition of an isotope. Same number of protons, different number of neutrons. You don't have to go in and even do the math. Okay, you don't have to say this one has, they each have 15 protons and phosphorus 32 has 12. You don't have to do the math. Nobody asked you to do the math. It doesn't say specifically to include the numbers, so you don't have to. Okay, so that's a perfect answer. Now, 52, they are not looking for any type of explanation. The line is this long. It helps you to figure out how much writing you actually have to do. And it's kind of like a random question. It says, determine the oxidation state of chromium in potassium chromate. Okay. For this one, I like to do something that I call a QCT chart. Okay. We're going to walk through this one together. Actually, I may pull up a window in Canva and do it over there to have like a little bit of scratch space. Also, I like their whiteboard a lot better than this Tammy. Don't love it. Okay. Whoop. Get over here. Okay. That formula was K2CrO4. Okay. Again, I like to do what I call a QCT chart. It is quantity, charge, total. Kind of the same way I like to do the formula mass. And I like to keep it this way to like kind of keep consistency. So on the left side, we're going to list all of the elements. We have potassium, we have chromium, and we have oxygen. That is the ugliest O anyone has ever drawn. Okay. Q stands for quantity, so we're just counting. We have 2 potassiums, we have 1 chromium, and 4 oxygens. The charge is kind of interesting. So we know that potassium is a member of group 1. So it'll always be +1. Chromium is literally what we're being asked about, but part of the reason we don't know this is because chromium's a transition metal. So we're going to leave that blank for now. And we know oxygen is always -2, every single time, no matter what. Now, what I want to do is go through and say, okay, all of my potassiums, both of them have a charge of +1, so collectively they would have a charge of +2. I have 4 oxygens, each at -2, so my total there is going to be -8. And then I have a total, okay? And because this is a neutral compound, my total for the whole thing has to be 0. But the question is, what goes right here to make the whole thing 0? And then what goes right here? All right, so in order to get this entire thing to be 0, inside this purple box would have to be a +6. And I only have one chromium here. So my one chromium would be +6 because the one chromium coming in at +6 would give me a total of +6. The reason I'm walking through that right now is because sometimes you'll have to do this for having 2 atoms, right? So then you'd have to take this number in the total column and divide it by 2, okay? So this right here, your thing would have to be +6. I would not get cute and then try to say that 6 is the same thing as +6. I would be very specific and write the plus. Now is not the time to be shorthand stuff. Ooh, you see this? Allow credit for +6 or 6+. It does not allow credit for just 6. Okay. Let's keep going. The first 4 elements in group 14 are carbon, silicon, germanium, and tin. These elements form compounds with chlorine that have similar formulas. 2 examples of these formulas include silicon tetrachloride, SiCl4, and germanium tetrachloride, GeCl4. State the general trend in atomic radius as these 4 elements are considered in order of increasing atomic number. That has almost nothing to do with that little blurb. Okay. So the general trend in atomic radius. We are talking about carbon. Where are we? Draw. We have carbon. We have silicon. We have germanium. And we have tin. Okay. This is asking what's the trend down a group. Ooh. Atomic radius increases down a group. It doesn't ask why. You don't have to explain why. Just the general trend. It gets bigger. In fact, you could look up some of these, all of these on table S. Table S kind of cuts out for a section there. Let's see. Whoop. Okay. Carbon, obviously we have silicon, we have germanium. It's 32. We have that radius, and tin is number 50. And we have that radius. So you could look it up. Down a group, the reason is because as we go down a group, each period is going to have a new principal energy level. So they're getting bigger. Okay. 54 asks, state in terms of electron configuration why silicon and germanium both form tetrachloride compounds. Okay. I would not actually use the word electron configuration to answer this question. But I would reference electron configuration. So hear me out. Each has 4 valence electrons. State in terms of electron configuration why silicon and germanium both form tetrachloride compounds. Each has 4 valence electrons, which bonds with chlorine's 1 valence electron. That would be my answer. But I'm a professional, so let's see what they are accepting as a proper answer here. Okay. All I truthfully wanted to put was this first line, was that they have 4 valence electrons, and that was it. Now, again, electron configuration, I didn't say the word electron configuration in my answer, but 4 valence electrons is specifically talking about a piece of the electron configuration, okay? So really what they're saying is that they want you to state that it has something to do with electrons and that it has nothing, not nothing, they just don't want you talking about they are in the same group of the periodic table, that's why. That's why they state those things the way that they do, okay? They have the same number of electrons in their outermost shell. Outermost shell is the same as valence. Also, if you like get really good at reading these, this one says germanium and silicon. This one says Si and Ge. Those are like interchangeable, right? They don't actually have to have the did you see the bug? There's a fly in the house, in case you missed it. My dog is hunting this bug. Did you find it? Okay, I guess not. If you get really good at reading these things are interchangeable. So you could put like germanium and silicon have the same number of outermost shell electrons. Okay, it doesn't have to be like super specific. Okay. Let's check out question 55. The equation below represents the reaction between ammonia and hydrogen chloride. Explain in terms of distribution of charge why a molecule of compound 1 is polar. Okay, NH3. You don't have to know anything really about NH3 in order to answer this question. You just have to know what makes something a polar molecule. So the quick thing would be SNAP. Symmetrical nonpolar, asymmetrical polar. If we have a compound that has an asymmetrical distribution of charge, it is going to be a polar molecule. Okay? So I am going to draw what the Lewis structure of ammonia looks like. You would have N with a lone pair bonded to 3 hydrogens. Okay? Because I have a hydrogen on the left and the right, we're fine. But when I look at the top and the bottom has a lone pair of electrons. Electrons are not the same thing as hydrogen. So this is an asymmetrical molecule, making it polar. Now, this specifically says, in terms of distribution of charge. So I would say, asymmetrical distribution of charge. That would be my answer. You could get like really in depth and say there's a lone pair on the top and there's a hydrogen on the bottom, but some people would draw it upside down and the lone pair would be on the bottom and the hydrogen would be on the top. My professional opinion after grading these tests for years is to write less. I have found that kids write a lot because they want to cover the base, right? They want to make sure that they hit everything. Sometimes they're not even really sure what they're writing and they just write and write and write and write and write. And you wind up talking yourself into a wrong answer. So if asymmetrical distribution of charge answers it, call it. Just stop. Now, if you want, we can look at the answer key. Molecule of NH3 is nonpolar because distribution of charge is asymmetrical. That's exactly what I wrote. The molecule has an uneven charge distribution. Same thing. The center of positive charge and center of negative charge do not coincide. I have never heard anybody describe it that way at all. Literally ever. That is the strangest answer I've ever seen. I don't think any student would write it that way. That's an adult writing that. So that's done. Okay, so that's it. Don't talk yourself too much. Now, for those of you who learned valence shell electron pair repulsion theory, you cannot use that to answer this question. You can't say that this is a trigonal pyramidal molecule. That's why. Because that doesn't talk about distribution of charge. Okay, so that's why it's not part of the answer key. Okay, 56. Draw a Lewis dot diagram for a molecule of compound 2. That's HCl. HCl is 2 nonmetals, so they have covalent bonds. This is going to be, let's fatten up this a little bit so we can actually see what we're working with. We have a hydrogen. It shares 1 electron with a chlorine. Let me draw this the long way so we can learn from it. Okay, so hydrogen has 1 valence electron. This is not how you write your final answer. Chlorine has 7 valence electrons, right? And chlorine wants to get 8 because chlorine is a big atom. It's going to follow the octet rule. Hydrogen is a little atom. It only wants 2 valence electrons because that's all it can hold. So hydrogen is looking to gain 1 and chlorine is looking to gain 1. And they compromise, right? Because nobody's willing to lose. So hydrogen says to chlorine and chlorine says to hydrogen, I'll share 1 with you if you share 1 with me. And what happens is that this is going to become a bond, a single bond, in fact. And you would draw it as a line, just like that. I'll share 1 with you if you share 1 with me. And that's the whole answer. Don't write on it. Don't put a partial charge on it. Do not do anything they don't ask you to do. Because if you mess that up, you're going to get marked wrong. Because it kind of shows that you don't know what you're doing. Okay? So that's the Lewis dot diagram. Don't overdo it. Okay. Identify 2 types of chemical bonds in the product of this reaction. Okay. NH4Cl is a weird thing. And that is because NH4 is a polyatomic ion. It's on table E. His mouse moves so quickly across the computer screen, but he scrolls so slow. Okay, table E, ammonium is right here. Boop, NH4, NH4 plus, right? And that is having a bond with a chloride ion, which is right there. Inside of this poly is covalent bonds. Nitrogen and all of those hydrogens are sharing electrons. They share electrons to the point where they're making an ion, which is kind of strange, but that's what it does. And the ammonium, is going to have an ionic bond with the chlorine. This is covalent bonds that form a poly, and that poly is going to, as an ion, is going to make an ionic bond with the chloride. So it is doing both ionic and covalent bonds, okay? This is a very nice way for them to ask you to fill in the answer. It is ionic and covalent. They don't want an explanation. They don't want to hear anything that you have to say. And I know that that sounds mean, but I'm trying to help you here. They don't want to hear what you have to say. The answer is ionic and covalent, be done. This is out of love, okay? I've seen a bunch of kids mess this up. Just talk too much. Have some confidence. Okay, question 58. This says, a sample of helium gas is placed in a rigid cylinder. Rigid cylinder is keyword for constant volume. It just means that it would be like this with a lid. Not like a squishy water bottle where you can, or like something with a movable piston or a syringe. Okay, those are things that you can change the volume of. This is chemistry hidden language for constant volume. Okay, but we have a movable piston. So if you have rigid cylinder on its own, that would be constant volume. But because we have this part that says movable piston, now we have a place where we can change the volume, okay? So we have like a syringe. We have a firm thing, and then typically it's like a rubber stopper, right? Let's just imagine it's this, and you could squeeze the stopper down, and then this would be the volume, and you could pull the stopper out, and then that would be the volume. Okay, I just shoved a whole fist in a glass of water. Okay, so because we have a movable piston, typically it also means that we're measuring this, okay? So we are no longer at a constant volume, but instead we have a changing volume. Because we have these two pieces together. We have the movable piston, okay? The temperature starts out at 25 Celsius. The volume is 300 milliliters, and the pressure is half an atmosphere. State in terms of the average difference between distance between helium atoms why the density of gas increases when the piston is pushed further into the rigid cylinder. Ooh, okay, that's a big one. The distance between helium atoms. why the density of the gas is going to increase when the piston is pushed further into the cylinder. Okay, I would call this question the 100 breaker if I had to guess. This, my guess, is the most missed question on the test. It is the question that is going to trip kids up, okay? Because there's a lot going on here. So if we shrink the volume, right, we're pushing the piston in. So if we have this much to begin with and we push the piston down, now we're squeezing all this gas together, okay? Density is mass divided by volume. We're going to have the same mass in a smaller volume. So this gas is going to become more dense. But they don't want us to talk about volume, and they don't want us to talk about mass. They want us to talk about the distance between helium atoms. Really what we need to say is that the helium atoms are going to be pushed closer together. And that is going to increase the density. And I would leave it there. But let's take a look at the answers that they accept. Ooh, look at this. Remember when I said at this right here that you had to turn it into a line? It says do not allow credit for a line with dots on the end. Because a bond is a line and each dot is an electron. You have to completely convert the dots into a solid line. Okay. Moving on. This says average distance decreases. Pushed closer together was my answer. Gas atoms are closer together, so the gas volume is smaller. A smaller volume means a greater density because the mass remained the same. That, I would say, is too much talking. And it's not that I don't think that you are a smart kid, because if you are here watching this video, it means that you care. And if you care, you're a smart kid. You're using resources to help you out here. That just by default means that you're a smart kid. My thing is that this is a 3-hour-long test. You are going to run out of brain juice. It's 85 chemistry questions. Your brain just melts through the process of taking the test. Give the smallest answer you can, okay? Because what happens is the kids try to write this and they slip up one word. Increase, decrease. It happens all the time. The shortest answer that you can come up with is my advice. Okay, smaller atoms. The atoms have a smaller average distance between them. Keep it simple, keep it short. Okay, 59. Determine the volume of the helium gas when the pressure is increased to 1.50 atmospheres and the temperature remains at 25 Celsius. Okay. Combined gas law. The combined gas law is on table T. Anytime you have to do math, you flip all the way to the back of the reference table. On table T, we have, where are you? Right here, the combined gas law. PV over T in situation 1 will be equal to PV over T in situation 2. Okay, that's what the 1s and 2s are for. But if any of these are constant, you pull them out. Okay, so in this case, we have a constant temperature. Our temperature is going to stay 25 the whole time. If you have 1 divided by 25 and 1,000,000 divided by 25, it doesn't matter because they're both divided by 25. They're the same on both sides of an algebraic expression. You don't need them, okay? So in this case, we are going to do the pressure times the volume before is going to be equal to the pressure times the volume after, okay? The pressure to begin with was 1/2 an atmosphere. And the volume was 300 milliliters, according to this thing. Come on. 300 milliliters. It's saying that the pressure is increasing to 1.5 atmospheres, and it wants to know what the new volume is. Okay? So, 300 times 0.5. It's 150, but plug it in anyway. So I'm getting 150 is equal to 1.5 times V. Divide both sides by 1.5 to get V by itself. And my volume is coming out to 100 milliliters. If you are unsure, my advice would be to do this. Write down the answer that you get. Wait, what? 300 times 0.5. Oh, and then, yeah, it would be 1.5 times 100. Yeah, okay. My brain was thinking that this should have come out to 100. I don't know why. You would plug in 100 here, right? And then you would do this. And make sure that they're the same number. And if they're the same number, then you're okay. I also suggest that you go back and redo the math again. Don't look at what you did originally. Do the problem from scratch and then compare your two answers. Make sure that your answer is correct. Because with the multiple choice, like, it's a lot easier. With these types of things, you want to make sure that you are getting the correct answer. The Regents exam, the Regents exam does not care about significant figures. If we were caring about significant figures, we would go out and put the decimal right there. 3 sig figs on the whole thing. But it does not ask you to solve to the correct number of significant figures. So if that's going to throw you off, at least for now, we're not counting them. I can't say what happens to the kids who take this next year in the future. June 2023, we're not looking for sig figs, okay? So it's 100. Okay, next up, question 60. Oh, compare the number of helium atoms in the cylinder. Compare the number of helium atoms in the cylinder at the pressure of 0.5 atmospheres to the number of helium atoms in the cylinder when the pressure is increased to 1.5 atmospheres by pushing the piston in. Nothing changed. The sample inside is still the sample inside, so the number of particles has not changed. It does not say that they added more helium. It does not say that they removed helium. All they did was take the helium and squish it. It's the same number of particles. It's the same number of helium atoms. The number of atoms has not changed. It is the same. They are equal. Nothing. Okay. 61. During a lab activity, a student places 21 mils of hydrochloric acid solution of unknown concentration into a flask. The solution is titrated with 0.125 molar sodium hydroxide until the acid is exactly neutralized. The volume of NaOH added is 18.5 mils. During the lab activity, appropriate safety equipment is used and safety procedures are followed. Okay. Explain in terms of ions why the hydrochloric acid can conduct an electrical current. Okay. HCl is a strong acid. And when you break it apart, it will look like this. It'll be H+. Come on, pen. And you will have Cl-. So that's it. You just have ions dissolved in the solution. Ions are dissolved for solution. They allow electrical current, which creates an electrolyte that can conduct an electric current. That's if you wanted to write it out nicely. The correct answers that they give are HCl has ions in the water, which are mobile. Ions in the solution move freely. Hydrochloric acid contains H+ and Cl- aqueous ions. It doesn't say specifically you have to state what ions are there. It would be nice to say that they dissolve ions. But here's the thing. It says specifically to explain. So you could not just write the equation. Okay, you could write the equation to support your answer. Again, I wouldn't, just in that be careful about writing too much type thing. Because if you did H minus and Cl plus and you just flubbed it up, then you would have a problem on your hands, because now whoever's grading your stuff thinks that you think that acids yield H minus, which they don't. H minus doesn't exist, right? So you could write that to support your answer, but I would just say there's dissolved ions and keep it simple. Okay. 62, determine the concentration of HCl solution using the titration data. Table T. We are going to do a titration. The molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. So we're going to pull that data from that little blurb up at the top. We have MV for acid is equal, oh boy, is equal to MV of the base. The molarity of the acid, we were told, is 0.125. We're going to multiply that by the volume of 21. Now, it does not matter what volume measurements go in here, whether it's milliliters or liters. Just make sure it's the same on both sides. Molarity here is unknown, and the volume is 18.5. So the molarities should be very close because the volumes are decently close. 0.125 times 21 is 2.625. And that is equal to 18.5 M. Divide both sides by the 18.5, right? And the molarity that I am getting is a yucky number, so we're going to chop it. You see how their molarity goes out 3 decimal places? I'm going to make mine go out 3 decimal places, because even though we're supposed to learn sig figs, they don't ask you to actually solve in terms of sig figs. So I'm going to put 142, because the 8 back there will kick the 1 up into a 2. So I'm going to say 0.142, and let's see if they agree. Excuse me, what? 142. How did I get the wrong answer? Did I mess something up? Oh, I did mess it up. No, I didn't. 21 milliliters of hydrochloric acid. Oh, that's the molarity of the base. I did mess it up. Look at that. Okay, strike that. Look at that. Okay, all this has to go. Boop-a-doop-a-doop. This is why you're supposed to write this out very nicely and gently. And truly, I'm rushing because I gotta feed the DOG. The molarity of my base is... Oh, and I have it... I still messed it up. Okay, the molarity of the acid is unknown. That's literally what the question is asking, Kelsey, you knucklehead. Okay. The molarity of the acid is unknown. The volume of the acid was 21. The molarity of the base is 0.125. You need to stop. Cut it out. Okay, so let's do this again. 0.125 times the 18.5 is 21M equal to 2.3125. Remember, you don't round until the very end. You don't have to write it all out, though. You can just keep it in your calculator. Okay, now I'm going to take that number and divide it by 21 to get M by itself, and now we're getting the correct answer. Okay, M is equal to 0.110, and that's where I would leave it because the next digit is 119. So there we go. And see, they even give you the units. Aren't they so nice? Sometimes. I don't want to give them too much credit. They're not that nice. Okay, 63. The table below lists the hydronium ion concentration and pH values for 4 different solutions in distilled water. The pH value is missing for sample 2. Determine the pH value for sample 2. Are they serious? Okay, so I guess they're asking you to do this by a pattern. Because to my knowledge, we don't teach the pH equation. Okay. Either way, my students would be prepared for this. I just didn't know that this was ever required. Okay. In order to solve the pH, the equation is actually pH is equal to the negative log of the hydrogen ion concentration. So in this case, to find out the pH value here, I would want the negative log of 1 times 10 to the negative 2. Okay, so looking at the table and looking at the pattern, you should be able to figure it out. But to do this in the calculator, you're going to hit the negative number. Then you are going to second. No, not second. Negative log. Negative log. Just as you see it there. It's going to give you a parenthesis, and you're going to do 1 times 10 to the negative 2. Close the parenthesis, hit enter. The correct answer is 2, right? Just like that. That is the answer. I would be fighting this question if I were a teacher in New York right now. Or in January, I guess. The pH there is 2. pH is the negative log of the hydrogen ion concentration. Hydronium, in case you forgot, it's on table E. Where are you? Hydronium. It's the first one there. Hydronium is really H2O that has that extra hydrogen ion stuck to it, and then it makes hydronium. Okay, so it's really that H plus ion that Arrhenius was talking about. It's just stuck to water now. Okay, so that's really what that is. Identify the ion released by the compound dissolved in sample 4 that allows the compound to be classified as an Arrhenius base. Okay, so Arrhenius bases, we know. What is going on? This mouse is so strange. The Arrhenius base, we know that that is going to be the result of dissolved hydroxide. Oh my goodness, my regular tricks don't work. Okay, that's going to be the result of the hydroxide, right? So here, our answer is going to be OH minus, or you could write out hydroxide. Don't do both, just pick one. You have to put the minus sign if you're going to write the OH though, okay? If you look at sample 4, NaOH, your only options were going to be Na or OH. OH is the ion, right? That's going to make it the base. Okay, then it says, state how many times greater the hydronium ion concentration is in sample 4 than it is in sample 5. So really, you're being asked to compare the pH values there. Okay, so sample 4, the pH is equal to 12, and in sample 5, the pH is equal to 13. Now, on the pH scale, one jump in either direction, right? The pH scale goes from 1 to 14. One jump in either direction is going to be a change in times 10. So if you are going down the scale from 13 to 12 to 11 to 10 to 9, you are becoming 10 times more concentrated with hydronium each jump. So one jump is 10, 2 jumps is 100 times more, 3 jumps is 1,000 times more. And the same is true for the base, but going up the scale. So from 1 to 2, 3, 4, 5, going up the scale. It's a little weird because it's the negative log. So you have the most hydroxide at a pH of 14, and we have the most hydronium at a pH of 1. Okay, so this is state how many times greater the hydronium ion concentration is. So it's asking how much higher it is in sample 4 than it is in sample 5, and the answer is 10 times. You have 10 times more hydronium in sample 4 than you have in sample 5. That whole explanation was for chemistry kids. Math kids, you would just look at this and say that it's a 10 times difference because you're very good at scientific notation. They accepted 10, 10, tenfold, and 10 times. So those were the answers that they allowed. Perhaps, I guess that's it. Okay. Moving on to part C, which is the final section of the test. Woohoo! Okay, part C is going to look like stuff you have never learned before, and they do that on purpose to make you upset. Okay. Boric acid. H3BO3 is heated to produce tetraboric acid, H2B4O7, and water. The equation below represents the reaction to form tetraboric acid. Okay, cool. Glad they gave us that because I didn't want to have to balance that. The tetraboric acid is then used to make borax, which is used as a cleaning agent. Borax is Na2B4O7 10H2O. It's a hydrate with a gram formula mass of 381 grams per mole. A hydrate is a compound with water within its crystal structure. Borax has 10 moles of water for every mole of the tetraboric acid. No. Of the Na2B4O7, whatever it is. Okay, explain why the formula for tetraboric acid is an empirical formula. Okay, tetraboric acid is this. H2B4O7. Let's draw that. H2B4O7. Okay, so we are asked to explain why that's an empirical formula. And the empirical formula is the simplest whole number ratio, like kind of lining up one element to the next, to the next, to the next. So 2, 4, and 7, those numbers together can't be simplified. So I would write the subscripts cannot be simplified or reduced. Or perhaps the subscripts already show the simplest whole number ratio of elements, and leave it at that. And let's see what they have to say. The formula is the simplest whole number ratio of atoms in the elements of the compound. The formula cannot be reduced. Okay, so I gave both of those answers. I don't see any other answer that could possibly work. Then it says determine the number of moles of boric acid that react in the equation to produce 10 moles of water. Ooh, I love this. Okay. So here is what I would do. We are going to do a mole ratio, and we are going to compare, and because this is my test and, you know, this is going on my transcript, I'm going to write all over it. We are going to circle water because that's what we're asked about. And we're also asked about boric acid, which is this one right here. Okay. Because these are formulas that I'm not really used to working with on the regular, I'm going to circle which one I'm talking about. Okay. So when I do a mole ratio, and everybody kind of sets theirs up a little bit differently, I always do what's given first. So I have 4 moles of H3BO3. And every time I do that, it is going to give me 5 moles of water. Okay? And I want to know how many moles of the H3BO3 I will need if I want 10 moles of water. Now, some of us are really quick and we already know the answer is 8 because 5 over 10 is 1/2. 4 over 8 would be 1/2, right? But for those of us who aren't quite there, you just cross multiply to solve this, right? So you would do the 4 times the 10. That gives you 40, right? Double bubble. 4 times 10 and 5x. So we would get 40. Whoop, come on. 40 is equal to 5x. Divide both sides by the 5, and you'll get 8. So 67, we are getting 8 moles. Whoop. And that is it. Question 68 says, show a numerical setup for calculating the mass in grams. Okay, that's it. We do not have to actually solve it. We just need to set it up, which I love. We want to know the borax. Okay. They've already given us the gram formula mass or the molar mass. It's 381. So I am going to say, oops, I need to write. This will be 0.200 moles is equal to X grams as 1 mole is equal to 381 grams. That would be an appropriate setup. There are lots of appropriate setups. You could do it like this. That's how I would set it up. You could also do like 0.200 times the 381 is equal to the number of moles, or rather the number of grams. There's going to be a lot of setups. I'll show you what they are accepting. Okay, so they say 200 is equal to X over 381, which is what I've set up. I just put the 0.200 over 1. You could multiply them with units. You could multiply them without units. And you could do the 0.2 times 381 over 1. Anything that's mathematically going to get you the right answer is going to be a correct numerical setup. It's a lot of preference. Okay, next up. Okay. I was just reading that note right there. Next up, 69. During a lab activity, appropriate safety equipment is used and safety procedures are followed. A student uses the lab equipment shown in the diagram below to determine the heat of combustion of candle wax. Heat of combustion is defined as the amount of heat released when a known mass of substance is burned and can be measured in joules per gram. At the start of the activity, the mass of the candle and water are measured. The starting temperature is 5 Celsius and the air temperature is 22 Celsius. The candle is lit and the water is stirred with a stirring rod. Several minutes later, the candle is extinguished and the student measures the temperature of the water in the can. When the candle is cool, the student measures the final mass of the candle. Lab results are shown in the table below. Okay. Oh, I love this. State the number of significant figures used to express the value for the mass of water. Okay, mass of water in the can is 190 with a decimal. Because we have a decimal, our decimal is present, we're going to come in from the Pacific side of the number. We start counting at the first non-zero number and count everything that comes after it no matter what. So for this question, we have 3 significant figures. Come on, baby. 3. State the direction of the heat flow between the air and the water in the can before the candle is lit. Okay, so the starting temperature of the water is 5 Celsius. It's the sentence right here. The starting temperature of the water is 5 Celsius, and the air temperature in the room is 22 Celsius. So heat is always going to move from high to low. In fact, everything moves from high to low. Even like light. Light moves from where it's light to where it's dark, and then it illuminates the darkness, right? So in this case, we are moving from the air to the water. And there is no ask of an explanation, so don't give one. Just give them what they want. Okay. 71. Determine the amount of heat absorbed by the water. Okay, so the water is not changing phase. It's changing temperature. So we will use the equation Q equals MC delta T. Where are we? Okay, so Q equals MC delta T is the one that we use when we're changing temperature. Q equals MHF and Q equals MHV are for phase changes. HF is going to be used when we are either melting or freezing a sample. And vaporization is going to be used for vaporizing or condensing. Okay, so because we're only changing the temperature, we're going to use Q equals MC delta T. Let's see. The mass of the water in the can is 190. C represents the specific heat capacity of water, which is 4.18. And that is right here. Specific heat capacity. It outlines actually, let's see, back here, that C stands for a specific heat capacity. Because it's water, it's 4.18. Sometimes, in the rarest of occasions, they have you do this for other other chemicals. It would be a different number for a different chemical. Delta T is the change in temperature. So the water started out at 5, right? And it ended... Oh. It did it all for us. Delta T is just 39. They have already calculated what the change was, so we don't have to do that. That's fantastic. I love that. So we're just multiplying these numbers. 190 times 4.18 times 5. And this number is in joules. And the reason this is in joules is because this number, that 4.18, is in joules per gram Celsius. Our temperature is changed in Celsius, although it doesn't matter because the delta T in Celsius and Kelvin, it's the same distance. Once you subtract the units, it's just a number. And the mass is in grams. So, grams. So the number I'm getting is 3971. I just want to check that key before I... Why is their number so much larger than mine? What the heck happened? Oh, I put in 5. It's not 5. It's 39. That's why. Oh, it's a good thing I checked. Here I am, circling it and writing the wrong thing. 190 times 4.18. 4.18 times 39. Okay, now I'm getting the right answer. 30,973.8. Okay. That's probably an acceptable answer. What did they say? Okay, anywhere, they're allowing 30. The correct answer is 31,000. And that's because of significant figures. It should have 2 sig figs because that delta T was just 39 with 2 sig figs. So the correct answer, like for real, should be 31,000. But they are accepting anything from 30,700 all the way up to 31,122. So like truthfully, because it's the Regents exam and I know that they don't ask for significant figures, I would have just written 30,974. And they write the units for you. That's what I would have written. Again, they're not asking for significant figures, so like you don't have to do it. That's why there's a range on the answer. Okay. Pause the video if you need a break. I'm pushing through. Okay. A process was developed in 1912 to produce ammonia gas from atmospheric nitrogen gas and hydrogen gas. Iron can be used as a catalyst. The equation representing the system at equilibrium is shown below. State the evidence from the equation that the forward reaction is exothermic. Okay, forward reaction means we're reading from left to right. The reverse reaction means we're reading from right to left. And that happens a lot in equilibrium, okay? So knowing that this is exothermic means that heat is exiting. Exo means heat is leaving. Endo means heat is entering. So I would write heat is a product. I would also maybe write that 98.1 kilojoules leaves the reaction. Something to that effect. The heat term is on the right side of the equation. Energy is a product. Energy term is on the product side. Perfect. Love it. Compare the rate of the forward to the rate of the reverse at equilibrium. This is the definition of equilibrium. They could be asking about any equation in the entire world. The blurb that they gave does not have any bearing whatsoever. They literally could just write, compare the rate of a forward reaction to the rate of its reverse reaction at equilibrium, and the rates are equal. That is what makes it equilibrium by definition. They are the same, they are equal. Those are the only two options. Question 74. On the labeled axes of your answer booklet, draw a potential energy diagram for the forward reaction represented in this equation. Okay. Because this is exothermic, heat needs to exit. And if it is exiting, this is how it is described. If it is exothermic, then it would be an exciting roller coaster. Okay? So if it is an exciting roller coaster, then we're going to start here and boop, and down there. It does not ask you to put in any numbers, so don't. Simply don't. They are accepting something like this, where the potential energy of the products is lower than the potential energy of the reactants, and that's it. We're not getting crazy here. Okay. 75. State in terms of moles of gases why the equilibrium shift to the right due to an increase in pressure on the system at constant temperature. Okay, so this is Le Chatelier's principles. Le Chatelier's principles say that the equilibrium... Okay, when you have an entirely gas system, which we have, when you increase the amount of gas, like you maybe pump it with a noble gas, or you increase the pressure, so you are like squeezing this reaction, shrinking the volume. When you increase the pressure, the reaction is going to shift, meaning either the forward or the reverse is going to be more prevalent. And in the case of this, we are going to shift to the side with fewer moles of gas to relieve the pressure. And that's it. If you lose pressure, then the reaction would shift to the left, in this case, to bring that pressure back. Okay, so the shift to the right, and it's based on the number of moles. So this has state in terms of moles of gases. So you can't just write this. Shift to the right would relieve added pressure because the products have fewer moles of gas. And that would be the answer, okay? So if we check this out, they say 4 moles of gas on the left and 2 moles of gas on the right. So the shift to the right relieves the increased pressure. There are more moles of gas on the left than on the other side. Fewer moles, comma, less pressure. Wow, that's a very short answer. Okay. Question 76. State what happens to the rate of the forward when iron is added. So going back to the blurb, you think, what the heck does iron have to do with this? Well, iron can be used as a catalyst. So catalysts are known for speeding up reactions. What happens to the rate of the forward? I bet you increase is just an answer choice. Or like a possible answer. Wow, okay. Adding the iron will increase the rate of the production of the product. The rate of the forward would increase. That's what I wrote. Forward rate increases. The NH3, the product, would be produced faster. Okay. Okay, before the year 1828, it was thought that organic compounds were produced only by living organisms and that inorganic compounds were made from non-living substances. Urea is an organic compound. In 1828, a chemist heated ammonium cyanate and produced urea, which is very soluble in water. The equation below represents the reaction. Okay, so we have ammonium cyanate being heated to form urea. I got formulas. Great. Okay. Identify the element present in urea that is present in all organic compounds. Guess what? That has nothing to do with the blurb at all. I'm telling you, they do it to upset you. You're getting to the end of the test. I know, baby. Almost done. The answer is carbon. They ask you these questions like this on purpose, okay? Next, it says, compare the formula mass of the two compounds in the equation. Well, you don't even have to do the math here. If you look at the chemical formulas here, right? We have two nitrogens in each. We have 4 hydrogens in each, 1 oxygen and 1 carbon. So they should be the same. They're isomers. The formula masses are the same. They have the same number of everything. And state in terms of molecular polarity why urea is very soluble in water. Well, if it's soluble in water, then it must be polar because like dissolves like. Because water is polar, it will only dissolve other polar things. And because water is polar, it will not dissolve non-polar things. And that's just like a random fact that you would have learned in chemistry at some point. And the thing here is that hydrogen bonds to oxygen, and we get these 2 lone pairs. And this area is very negative, and this opposite side is very positive. And because we have that partial positive, partial negative, we are going to have a polar molecule. It's asymmetrical. Okay, so they have similar polarities. They're both polar. Urea is polar. Okay. Oh my goodness, we're up to question 80. Thank goodness. Are you tired? I'm tired. I'm gassing out. Okay, when a voltmeter is connected in the circuit of a voltaic cell, an electrical measurement called voltage can be read on the meter. The voltage of a cell is affected if the concentration of the solute in the half cells is changed. The diagram, the net ionic equation, and the graph below represent a copper-zinc cell. You're probably going to get a voltaic cell on the test, like 2 to 3 questions. It's nearly every test. When the switch is closed, electricity flows through the circuit as the cell operates at constant temperature. Okay, so we have a diagram, we have a graph. What do they want? Based on the graph, love it. Determine the voltage of the cell if the copper 2 nitrate aqueous concentration is 1.5 molar. Okay, sweet. Copper plus 2 is what is in the copper 2 nitrate. So we will take a look at this dot at 1.5 molar. And we will across over here, and we are getting, I don't know, 1.105, perhaps. That's what I like for my answer. Obviously there's a range to this, so let's see what the range that they allow is. 1.102 to 1.108. I am right in the middle there. Perfect. Okay. You don't even have to know any chemistry for that. That was just a table question, which we love. The first 30 and then these like table type questions, piece of cake. Okay, write a balanced half reaction for the oxidation of zinc that occurs in this operating cell. Okay, oxidation of zinc. Oxidation. Leo says grr. right? Oxidation is the loss of electrons. LEO, lose electrons, oxidation. So we would have a zinc atom with a 0 charge becoming a zinc ion. And zinc has to be +2 every single time, but it tells you right here, okay? So actually, this is really nice because it's telling you to look at zinc. So you would be looking at this and this, right? The zinc atom and the zinc ion. This is balanced in terms of mass, but you also have to balance it in terms of charge. And when you balance it in terms of charge, you're only using electrons, and electrons are negative. So if you had put electrons over here, let's just say, right, those 2 electrons, you would have a -2 on this side and a +2 on this side, and we don't want that. If we put our 2 electrons over here, then this +2 of the zinc ion would cancel the -2 of those electrons, and you'd have 0 as your net charge on both sides. Well, that is the reaction, okay? When one of the years I was teaching, I had a really great group of kids, and they taught me something very cool. They said, instead of Leo says "ger," we need the minus sign. They wanted it to be Leo says "girl," but spelt funny, like with an E. Okay, so Leo is lose electrons, oxidation, and they wanted it to be girl, Gerl, gain electrons, reduction, left. If you are writing a reduction half reaction, then the electrons would be on the left because they're being gained, right? Gaining electrons is reduction. Gaining electrons, you'd have to put them on the reactant side because they're being gained. If you're losing them, they're going to be on the product side, okay? And the idea is just make sure you get enough electrons to balance everything out so all of your charges add up to the same number. Sometimes they'll add up to 0, and other times they'll add up to a negative number. Just make sure that they add up to the same number. That's all you need. Okay, this is the last section, guys. Whew. Synthetic radioisotopes may be made by bombarding other nuclides with neutrons. The equations below represent a sequence of reactions converting stable iron-58 to cobalt-60, which is used in medical treatments. Okay. State the neutron to proton ratio for an atom of Fe58 in equation 1. Okay, this one is strange. I've never seen it written like this before. We are talking about this thing right here. That number, remember, on the top is the mass number, which is the sum of protons and neutrons. So P plus N is equal to 58. My protons for iron is that 26. Don't believe me, look it up on the periodic table. And that means that the neutrons have to be the difference between those two numbers. 58 minus the 26 will give me 32. So my ratio of neutrons to protons means that neutrons have to come first. 32 to 26, or you can do it as a fraction. 32 to 26. Or you could literally write 32 to 26, okay? You could also put like the P for proton and the N for neutron. You could. I don't see if that helps or hurts. Oh, and they allowed you to reduce it. I wouldn't. You know why I wouldn't? Because you put this in the calculator and you hit one button wrong and you're like gassed out, tired, it's question 82, and you're done. It did not say it had to be the simplest ratio. It didn't say it had to be, you know, the lowest whole number. It doesn't say. So don't bother. I wouldn't. Okay, state in terms of elements why equation 2 represents a transmutation. I'm just writing the rest of them here. Okay, this is a transmutation because one element changes into another. That would be my answer. What do they accept? 83. An atom of iron is changed into an atom of cobalt. One element is changed into a different element. Perfect. 84. Identify the particle represented by X in equation 3. Okay, I'm going to rewrite equation 3 down here. Give you some room. We have 59, 27 for cobalt. Oh, what does the answer booklet actually look like? Oh, I was hoping it gave you a blank space. It does not. Okay. We are going to add that to anonymous X, which is going to have a number at the top and a number at the bottom. And that is going to turn into cobalt, still with a 27, but with a 60 on the top. Okay. I like to set this up like it's algebra. 27 plus mystery number equals 27. Mystery number here is 0. Just basic algebra. Okay, 50 plus mystery number equals 60. Well, that would have to be a positive one. What has no atomic number but has a charge of +1? I'm not sure. Let's take a look at that reference table. Let's go back to that one that's all about nuclear stuff. What has a 0 on the bottom and a 1 on the top? Did you find it? It's this handy dandy neutron. They don't want you necessarily to write 1 over 0n. They want to identify the particle. So I would say the answer is neutron. Let me just go through and do this. 32 to 26, we said, and one element changes into another. Okay. Let's see what they accept. Oh, they do accept it. Oh, they accepted just N. I would not do that. No. If you write it ugly and it looks like an H, no good. You don't want to do too little, that it's like nothing at all. Okay. This is confusing to me, this book. Okay. One sec, buddy. Okay, last question. Determine the fraction of an original sample of cobalt-60 that remains unchanged after 15.813 years. Okay, we are going to do my method for doing this, okay? We split this. Up top, we have the amount, and in this case, it's going to be a fraction. You can also do this as a percent or mass. And on the bottom, we are going to do time. And in the case of cobalt-60, the amount of time is going to be years. At time equals 0, right now, this is going to be a fraction of 1. And then we're going to do 1 half-life, and we're going to look up the amount that is. But the fraction is going to be cut in half. And then it's going to be cut into a quarter. And then it's going to be cut into an eighth. Whoop. And then into a 16th. And then into a 32nd. Blah, blah, blah. The half-life of, the half-life of cobalt-60. That's what we're looking at? Cobalt-60. Cobalt-60. Right here. 5.271. Okay, across the bottom each time, we're going to add 5.271. So that right there, 10.542. So this is the first half-life. This is the second half-life. This here is the third half-life. Okay? Again, we're going to add 5.271. And at that point, that's where I get the 15 that they're asking about. 15.813. Oops. I don't have to continue because that is all I need, which means that my fraction is 1/8. Okay? It specifically asks for a fraction. Determine the fraction. But then, the booklet, the answer key, says that you can provide 1/8, 0.125, or 12.5%. don't allow that to become a habit, because my assumption is that this question was probably contested by teachers saying like, hey, you asked this question and you gave way too many answer choices. You allowed too many answers, and that's just like not the right thing to do. If you ask for a fraction, the answer should be a fraction. If you ask for a percent, the answer should be a percent. If you ask for an amount, it should be an amount. This doesn't even have a unit. This, I don't understand this. So if it asks for a fraction, make sure you're reporting your answer as a fraction. If it asks for a percent, report as a percent. I would keep that 1/8 and not do anything more than that. Do what it asks. Okay. I will be doing another stream at some point this week. So I'll decide on a time. If you subscribe, the like preview, Kelsey's doing a stream at this time, will show up in your feed. Feel free, of course, to leave any comments you have. I think that's it. Thanks for being here. Thanks for working with me. I will see you soon. Good luck on your test. And that's it. Have a good one.